audible?
Okay, fine.
Good morning, everyone. Myself, Dr. Ankit Kumar Mittal. I am one of the organizing secretary of first AIP hands-on training on quantum leap DFT code mastery, and I welcome you all to this workshop. And I am also acting as a chief counselor of North Zone. So now I would like to welcome all the speakers and dear President Dr. Sanjay Singh and Dr. Deepak and Dr. Captain Sir for this workshop. Further, we have with eminent speaker with us, and so now I would like to invite Mr. Ben Jamir for the brief introduction about the Association of Indian Physics. Mr. Ben, over to you.
Am I audible?
Yes, you are audible.
Okay. So, good morning, everyone. Respected Professor Rajeshwar Singh, founder and president of Janardhan Singh Foundation, our beloved Dr. Sanjay Singh Kumar, founder and president of the Association of Indian Physicists, our principal coordinator of AIP, Dr. Captain Utrat Singh, honorable expert for the morning session, Dr. Arun Kumar, respected Dr. P. Deepak, of this DFT workshop and his esteemed team, respective chief counselors, and all the participants. Firstly, I offer my sincere gratitude to the organizers for giving me this opportunity to highlight a few key aspects of AIP. The Association of Indian Physicists, also commonly known as AIP, is more than just an organization. It's a passionate community dedicated to advancing the field of physics and nurturing scientific excellence. Founded under the Janardhan Singh Foundation and supported by the Ministry of Corporate Affairs in India, AIP operates as a non-profit entity with its headquarters nestled in Barnala, Punjab. Our vision at AIP is clear. We aim to propel physics forward, foster collaboration, prioritize education and outreach, create a global impact, recognize excellence, and make a meaningful societal contribution. Our mission is equally robust. We strive to deepen the understanding of physics, encourage research and education in the field, and provide a platform for physicists worldwide to connect and share their discoveries. Led by our esteemed founder and president, Dr. S.K. Singh, AIP boasts a vibrant community of over 800 members and 23 council members spanning across the entire globe. Together, we contribute significantly to India's physics knowledge base and research endeavors. To ensure widespread access to physics education and research, AIP has strategically divided itself into more than 9 zones across India, each overseen by a chief counselor. These zones play a vital role in implementing AIP's vision and goals at the grassroots level. We're committed to excellence in physics education, which is why we organize a diverse range of events, from engaging public lecture series to dynamic seminars, conferences, workshops, and hands-on training sessions. As a proactive and forward-thinking organization, we have crafted progressive programs like our mentorship program, designed to support students who may face challenges in their educational journey. AIP takes immense pride in our AIP clubs established in various institutions across the nation. These clubs serve as hubs for motivating and educating students, fostering scientific curiosity, and promoting collaborative research efforts. We extend a warm invitation to individuals who share our dedication to advancing physics education and exploring new frontiers for the betterment of our nation. Let us join hands in a collective effort to cultivate scientific excellence and embark on a journey of growth, enriching our understanding of both the scientific realm and the academic landscape together. Thank you. Now I hand over to Dr. P. Deepak for the opening remarks on the workshop. Over to you, Dr. Deepak.
Good morning, one and all. Hi, Dr. Pukram Deepak, the Chief Counselor of AIP Central Zone. So I welcome you all in this auspicious event. That is first AIP hands-on training on quantum leap DFT code mastery. So this is jointly organized by the AIP and the JS Foundation. As we know that the hands-on training nowadays become one of the most important part of our learning, teaching and the learning. So hands-on training provides the predictive power, efficiency, then versatility, understanding of chemical bonding, then skill development, then problem solving abilities, confidence building, then retention of knowledge, adaptability and flexibility, feedback and improvement, as well as the preparation for the real world challenges. So looking all these points, it is very much required that the hands-on training has to be organized in a very regular basis in order to improve the quality of teaching and learning as well as the research. Now, why we need to study the density functional theory, or why we need to organize this workshop based on the density functional theory? Because we know that doing an experiment, it costs a lot of financial support, needs a lot of financial supports. Okay, and there are certain experiments that which we cannot be performed or we cannot do in our real life. So by using the computer-based experiment, we could easily determine the material property of a given material. Say, such as it might be in case of DFT, it may be your electronic properties. Okay, then band structure can be easily be plotted, and we can know whether the given material is the N type or a P type, or it's a half metal or half spin metal. So this is a very powerful tool. The DFT, this density functional theory, it's a very powerful tool. It provides the predictive power, then also efficiency, develops a new methods, and last one, very important, is environmentally and industrially applicable. Now, above this, I also thank the invited speakers, that is Dr. Deepak Upadhyay, Dr. Arun Kumar, Dr. Upendra, Mr. Kausal, and Saksam Nakotyal. All these invited speakers are welcome to our platform, AIP. So, a briefing about today's event. Dr. Deepak Upadhyay is a postdoctoral fellow, Faculty of Mathematics and Natural Science, Cardinal Stephen Wensky University, which is also from Poland. He will be talking about the quantum espresso on electronic properties of optimized structure, band structure, and density of state. Especially, he will be talking about aluminum-based material. Then Dr. Arun Kumar is an assistant professor at Department of Physics, Government PG College, Bilaspur, Himachal Pradesh. And Dr. Arun will be talking about SISTA, or in that he will be talking about structural and electronic properties of a material using the DFT code. Then Dr. Upendra, assistant professor, Department of Physics, IIT Allahabad, will be talking more about the N2K, electronic property of a cubic fluoride, that is cerium oxide. The Kausal, assistant professor, Department of Applied Physics, Maharaja Sayaji Rao, University of Baroda, Gujarat, will be talking about ORCA, electronic chemical properties like HOMO-LUMO structure, FTIR spectra, UV visual spectra. And lastly, Dr. Saksam Nakotyal, assistant professor, Department of Science, Naval Institute of Management, Ghaziabad, will be talking about ball strap. From this ball strap, you will talk about the calculation of the thermoelectric properties, electrical conductivity, then Seebeck coefficient, electronic thermal conductivity, which is one of the very important phenomena, one of the very important topics that in order to harness the heat energy into the electrical energy, this will be talk about the Saksam. So I welcome you all the participants of today's event, that is hands-on training for the DFT. So here I over to Ankit sir. Hello, Ankit sir. Hello, am I audible?
Yes, please.
Okay. So as Ankit sir is out of the contact, means a network issue. So I proceed with today's event. I hand over to the Chief Patron in Chief JS Foundation, Dr. Rajeshwar Singh, Founder President of JS Foundation. Sir, please. Is Professor Rajeshwar Singh is online?
Yes. Am I able? Am I audible?
Yeah. Audible, sir.
Okay. Ladies and gentlemen, I am Dr. Ayesho Singh, founder president of Janardhan Singh Foundation. I extend a warm welcome to you all to this hands-on training on quantum leap DFT code mastery. This program is jointly organized by Association of Indian Physicists AIP and our foundation. Today marks a milestone in our commitment to advancing scientific excellence and innovation. The Janardhan Singh Foundation has always prioritized education and research in the education, more especially in the area of physics. This training program exemplifies our dedication to providing practical learning experiences. By partnering with AIP, we aim to equip participants with the skills needed to excel in DFT code mastery. This event is not just about learning, it's about empowerment. The participants will certainly gain the tools and knowledge to tackle the complex challenges, issues, and contribute meaningfully to the scientific research and advancement. I am grateful for the collaboration with the Association of Indian Physicists. Together, we are empowering the next generation of physicists to push boundaries and drive innovation. To the participants, I will urge to approach such type of opportunities with very enthusiastic and determination. Mastery of DFT codes opens doors to new frontiers in science and technology, embraces the challenges, embrace the learning process, and let your passion for discovery to guide you. As the founder president, I am proud of work being done by the various members of Janardhan Singh Foundation in partnership with AIP. Together, we are shaping the future of physicists, and I have no doubt that the impact of this training will be felt for years to come. Also, I extend my gratitude to all the organizers, sponsors, and participants for their contributions in this workshop. Your dedication to advancing scientific knowledge is commendable, and I am confident that we all together we will continue to make great strides in the field of physics. Thank you, and may this training program be a resounding success. Thank you, and Jai Hind. Thank you.
Thank you, the founder president of JS Foundation. Next, I hand over to the remark of Patron, Dr. Sanjay Kumar Singh, founder president of AIP. Hello, Sanjay sir, are you present?
Yes, please.
Sir, please proceed.
Yeah. Thank you, Dr. Deepak. Respected Chairman, sir, of Janardhan Singh Foundation, Professor Dr. Rajeshwar Singh, sir. Today's speakers, Dr. Arun Kumar, sir, Dr. Deepak Upadhyay, sir, and distinguished participants from all over the India, and my heartiest council members of the Association of Indian Physicists. So on behalf of AIP, I, Dr. Sanjay Kumar Singh, President of AIP, I heartily welcome you all in this unique event, that is DFT code mastery. I'm very sorry for not taking part dedicatedly in this event due to some mishappening in my family. I will try to present to learn from the expert. I personally request from all participants to take part dedicatedly in this training, and please keep in mind that you all are collaborator of AIP, not just participants of this two-day event. Please don't be panic when you are not getting clue for particular things from this event. We all are always with you for any help apart from these 2 days event. Please try to get more knowledge from this event and have passion to serve the nation in an innovative way. I assure you, you will get lots of knowledge from this event. Once again, I thank you for your participation in this event. Over to you, Dr. Deepak.
Thank you, sir, for your kind words. So next, I call the Principal Coordinator of API, Dr. Captain Rituras, for a few words.
Thank you so much, Dr. Deepak. So first of all, very good morning to all of you. As Dr. Sanjay mentioned, I believe you all will enjoy this workshop beyond your expectation. So today I stand before you to share the excitement surrounded by this workshop. And this could not have been possible without your thirst of knowledge and learning attitude. The workshop promises to be a transformative experience for all the participants, whether you are a faculty member, research scholar, or a curious student. This workshop is designed to benefit you all. With the effort of the AIP family, we are making it a place where theory meets practice, equation transformative solutions, and curiosity fuels discovery. With this, I welcome you all to the hands-on training workshop on density functional theory and related computational package. Thank you all and happy learning.
Thank
Dr.
you, sir.
Deepak.
Thank you, sir. Next will be is the lecture section. It will be delivered by the Dr. Arun Kumar. So this session will be comprised of two sets, 45 minutes for the theoretical background and 120 minutes for the hands-on training. So briefing about Dr. Arun Kumar. Dr. Arun Kumar is an assistant professor at the Department of Physics, Government PG College, Bilaspur, Himachal Pradesh. Dr. Kumar obtained his PhD in 2014 from Himachal Pradesh University, Simla. His thesis title is Structural, Electronic, Optical, and Transport Properties of the Crystalline and Alloy Thin Film Nanowire of Noble Metals. Dr. Arun also obtained his MPhil in 2008 Himachal from the same university, and his thesis title is AB Initio Calculation in Condensed Matter Physics, Theoretical and Condition. In 2006, Dr. Kumar obtained his MSc from the same university. Dr. Kumar is presently working as the assistant professor from 2009 to 2016 in Government College, Bansgarh, District Kulu, Himachal Pradesh, from 2016 October to September 2022 at Swami Vivekananda Government College. From 2022 to till that, he worked in PEC, College, Bilaspur District, Bilaspur, Himachal Pradesh. Dr. Kumar has a research interest in condensed matter, which includes theoretical and a computational material science, material modeling using DFT, functional theory, that is properties and prediction. Dr. Arun has guided one PhD student and 12 MSc projects. Dr. Kumar is a well-known speaker, attend more than 11 invited lectures. There are a lot more to say, but due to the time constraint, I will be handing over the programs to Dr. Arun Kumar. Thank you, Arun Kumar, for accepting our invitation.
Thank you, Dr. Deepak. I thank all the organizers to inviting me for this wonderful workshop. So, am I audible?
Yeah, audible, sir.
Okay. So, can I give me some feedback about the participants? That from which background they are very beginner or they are little bit advanced?
Sir, it's a mix. Some of our
Okay,
somewhat in the
so I will
middle
start with the very basic and
Yes, sir.
try to switch over towards the density functional theory. So
Yes, sir.
let me share my screen. Mm, just yeah, it's there. My screen is visible.
Yeah, it's visible.
Okay, that's it. So the talk of my so the title of my talk is structural and electronic properties of materials using DFT code. So here I will talk about briefly that what type of density functional theory codes are available and how they do the calculations. Uh, so let me first of all begin with the Schrodinger wave equation. So all of us are familiar with the Schrodinger wave equation. And if I try to look at the Schrodinger wave equation, it is like this, that H psi is equal to E psi. It is the Schrodinger wave equations. And our objective is to simply solve this Schrodinger wave equation. Yeah. So our objective is to solve this Schrodinger wave equation, and it has two very interesting terms which are there. So first is this E eigenvalue of energy, and another is the wave function. So in most of the cases, either it is a free particle problem or harmonic oscillator, our objective is to find out the value of E and psi. So psi is a eigenwave function and E is the eigenvalue of energy. So, but to solve this equation is a very difficult task. As we all of are the physicists or few maybe from the chemistry background, so we know that we have solved the Schrodinger wave equation exactly only for the hydrogen atom, and for rest of the systems, means the for rest of the materials, we have to solve this Schrodinger wave equation with the help of various approximations. So, but before talking about the various approximations, I will talk about that why energy and why wave function is important to us. This is a very basic question which I would like to ask to myself. So let me go to the next slide. So why energy is so important? So if I try to look at this particular plot, this is for the bulk gold. So as we know that bulk exists in the FCC lattice. So that means if I plot energy versus lattice constant graph, then we can estimate the actual structure of the system in which it is occurring in the nature. So if I look at, means I tested gold in various structures. First of all, I tested it with the simple cubic, then body centered, then FCC. And in every case, I am getting the minima when I am changing lattice constant. Here I am getting the minima. In this case, I am getting minima here. And after that, I am getting minima here. So, but if I compare all the minima, then FCC is the lowest most. So that means gold exists in the FCC lattice. And this graph I have plotted with the help of density functional theory. I used the Siesta code, and on the basis of that, I confirmed the FCC structure of gold. This is the one thing, right? And after this, so that means energy versus lattice constant help us to estimate the structure of the material, right? This is the one thing. And another is the cohesive energy. So this is again for the bulk gold. So what I did, I keep on increasing the lattice constant slowly and steadily. And what I found, when the lattice constant is around about 14 angstrom, then energy converges to a particular value. And here, this is the energy corresponding to minima. And if I compare these two energies, then this is the cohesive energy of this gold. So this is the estimated value, and this is the experimental value. So this is in closer resemblance with the experimental value. So that means another very important thing we got, it is the cohesive energy. Then third important thing is the bulk modulus. Bulk modulus tells us about the strength of the materials. So if I plot, so if I plot volume versus energy graph, then it tells us about the bulk modulus. Then another very important thing which we have to keep in mind, it is the energy versus K graph, E versus K graph. It tells us about the band structure. And this electronic band structure of gold, it resembles with the experimental values. So that means this is the one aspect of energy. Once we got the energy from the solution of the Schrodinger wave equation, then it tells us about the structure, its nature, its cohesive energy, its strength, and the most important thing is that is the electronic band structure. So that's why E is a very important parameter giving the solution of the Schrodinger wave equation. Then another very important thing. So if we take a derivative of energy with respect to the various positions, atomic positions, or the applied electric field, then we can calculate so many other parameters. Like if we take a derivative of energy with respect to R, it tells us about the forces on the nuclei. And if I take a second order derivative with respect to different positions of the atoms, then it tells us about the force constant, vibrational frequencies, infrared, and Raman spectra, etc. And if I take a third order derivative with respect to different positions, then I can calculate, or one can calculate, the vibrational frequencies. And if we take a derivative with respect to the electric field, then we can calculate the dipole moment. Similarly, if we take a second order derivative with respect to, first of all, positions and then the electric field, then we can calculate the infrared intensities. Similarly, we can calculate polarizability, light scattering, hyperpolarizability, and the second harmonic generations. These are the few properties which are related to energy. So that's why we are most of the time interested to calculate the energy of the system. So once energy is there, then we can estimate various types of properties and the behavior of the system. And for this, you can go to this reference and you will get all these values. Means all this stuff is there. So, then next is the why wave function is a very important thing for us. So the wave function in quantum mechanics, it basically describes the behavior of the electron in a atom or a molecule or in a material. And what wave function provide us? Wave function provide us the probability of finding the electron at a certain position. And this information basically used to calculate the charge density or charge transfer within the system. And the wave function can be used to determine the types of chemical bond present in the molecule or the material. So that means what we are getting information once we are having the information of the wave function. Wave function, or in other words, we can say that psi star psi. Once that is there with us, then we can have the estimate about the charge density, that how the charge is transferred within the system, which atom is gaining the electron or the charge, which one is losing the charge. And after that, this information help us to estimate the type of chemical bond, whether it is a ionic bond or a covalent bond. This type of information can be obtained from this. So here it is the difference of the charge density, which I did some calculation for the nanoflake, and this nanoflake is CR6S40. So then now the next is that how to solve this Schrodinger wave equation. This is a very important question. So there are different aspects to solve this differential equation. So this is the Schrodinger wave equation, and so the very first approximation is the Born-Oppenheimer approximation. In Born-Oppenheimer approximation, what we do, as we know that the mass of the electron is a very small as compared to the mass of the nuclei, and the nuclei is almost stationary, even that is vibrating about their position, but in comparison to the motion of the electron, the nuclei seems to be stationary. If we consider that, that means the motion of the nuclei can be freezed and only the electronic motion can be considered. So this is the very first approximation which we have to consider. So that means in this, their kinetic energy can be freezed, because this term is basically kinetic energy of the nuclei. So that means nuclei can be freezed here. This is the very beginning approximation. Then after that, there comes the Hartree approximation. And what do we do? So if we are having a multi-electron system, then how the multiple electrons can be treated? So for that, wave function for the multi-electron can be written as the product of individual electrons. It's like this. It's a very simple layman language. And all the electrons are assumed to be independent. And they all are independent, but they are moving under some effective potential. That's what we do in the Hartree approximation. But there is a problem with the Hartree approximation. The problem is with that is, as we know that psi is psi for electron, it must be antisymmetric. It is antisymmetric, but Hartree do not consider antisymmetry. he ignored anti-symmetry. So to incorporate anti-symmetry into it, Fox suggested that the wave function, multi-electron wave function, cannot be simply written in the form of a product, but it can be written in the form of a Slater determinant. For example, if we are having a wave function of 3 electrons, then that can be written as psi1 r1, psi2 r2, and psi3 r3, and sorry, psi1 r1, psi1 r2, and psi1 r3, and then psi2 r1, psi2 r2, and psi2 r3, and similarly psi3 r1, psi2, sorry, psi3 r2, and psi3 r3. So that means the wave function can be written like this, and there is some normalization constant is also sitting here. Means if I am writing something in the form of a determinant, it's a very important thing. Then that automatically take care anti-symmetry. Now, let me ask one question, that why something written in the form of a determinant can take care anti-symmetry? Because when something is written in the form of a determinant, there is a property of a determinant is that when we swap two rows or columns, say I am swapping this to this to this, then what will happen? Automatically, negative sign comes into picture when we do calculation in the form of a determinant. So that means this is a way that how Hartree folk considered this, what we call anti-symmetry, right? So that means anti-symmetry is taken care. So two things are there. One thing is that in the Born-Oppenheimer approximation, we have freezed the nuclei. Only electron motion we have to consider. Then in Hartree, how to treat the multi-electron systems? For that, we have to write down the multi-electron wave function, simply treating all the electron as the free electrons, and they are moving under some effective potential, and the wave function can be written simply in the form of a individual electron wave functions. And to take care anti-symmetry, we have to write down the wave function in the form of a multi-electron wave function can be written in the form of its Slater determinant. But even then, there is a problem. There is a that how to deal with the, because since the electronic wave function is still very difficult. Schrodinger wave equation, electronic Schrodinger wave equation is still very difficult to solve. So for that, we have means there are two problems main. One is the how to deal the 3n variable problem, and another is the correlation energy. And what is a correlation energy? Exchange and correlation, दो terms हमारे पास आती हैं. These are the two terms, exchange and correlation. So electron is a very typical thing. Means when two electrons are sitting together, they generally repel each other. Coulombic repulsions are there. But अभी तक हम spin की बात नहीं कर, we are not talking about the spin. But when we consider the spin, so that means two electrons, when same spin are sitting together, then they will repel. But if two electrons with opposite spin, they are sitting together, then they will try to attract each other. So that means this type of behavior is known as exchange and correlation collectively. So mathematically, how to tackle this? This is still a very difficult task. So these are the two difficulties we are facing. One is the 3n variable. So for that, a new approach has been developed that is known as the density functional theory. So what we do in the density functional theory, in density functional theory, we replace many particle wave function with the electron density. Means we are not taking individual electrons as a, but we are considering their electron density, that how they are arranged all the electrons as a whole, means we are considering their electron density. So that means this new approach is known as the density functional theory, and this is basically a wave function for the many electron systems. So what is density functional theory? Let me come back to it. So density functional theory, first of all, the main fundamental pillar of density functional theory is the Hornberg-Kohn theorem or Hornberg-Kohn formulation, and they have given the two theorems. First is the first HK theorem and another is the second HK theorem. So there is one-to-one mapping between ground state electron density and ground state wave function. So that means ground state electron density corresponds to the ground state wave function. That's the meaning of it. And once we know the ground state density, that means, and it minimizes the, means ground state electron density, it minimizes the total electron energy of the system. Then to practically implement density functional theory to the real systems, uh, Kohn and Sham gave another formulation. So what they suggested that ground state charge density is given as a sun over one electron orbitals, and they are known as Kohn-Sham orbitals. They are not real orbitals, but they are the Kohn-Sham orbitals. And reformulation of the Schrodinger wave equation of equation of interacting electrons moving in an external ion potential into a problem of non-interacting electron moving in an effective potential. Means one electron orbitals, they are all are non-interacting, but they are moving in some effective potential. That's what is suggested by the Kohn and Sham. So this is the Kohn-Sham formulation basically. So this is the kinetic energy, this is the effective potential in which electrons are moving, and this effective potential is basically this one, means it is the effective potential, ये Hartree potential, and it is the exchange correlation potential. So it, if I try to look at it, then it has two parts. One is this one and another one is this one. So kinetic energy, it is the kinetic energy, and this is the Hartree potential, and this is the Coulomb energy, and this is the most critical part which is there. This is the exchange correlation potential, and it, this, to consider or to estimate this part is a very difficult. So let me come to the every term separately. So this is the first is the kinetic energy term. It is calculated using the Kohn-Sham orbitals. So to solve this, we will use Kohn-Sham orbitals. These are basically mathematical. Then Hartree potential, it describes the interaction between the electrons in the system and is approximated by the Coulomb potential arising from a system of fixed electrons. Then Coulomb potential, it defines the interaction of an electron with the different atomic nuclei present, and to take care this one, we'll use a trick which replaces Coulomb potential by a pseudo potential, right? So in various codes, there are different codes we are having where we will use a pseudo potential approach, and there are certain codes which will use the full potential. So I will talk about these later on. Then exchange correlation. So the most important potential term in the Kohn-Sham equation is the BXC, and there are various efforts have been made to estimate this. So first effort is the local density approximation. And
Hello,
this
sir.
approximation,
Sorry to interrupt. I have one
yeah,
question. This Coulomb interaction and Hartree, Coulomb potential and Hartree potential. So in short, we will say Hartree potential is that consider the interaction between
electrons.
electrons,
Yeah,
and
yeah,
Coulomb potential we especially define for electron nuclei interaction.
electronuclear interaction.
And in Hartree
Right.
potential, we are assuming all the electrons are fixed, and then we consider the potential between them, like that.
Yeah, yeah.
And in case of nucleus is already heavy, so in that also we assume electron as a fixed or nucleus as a
No, no,
fixed.
nuclei as a fixed.
And electron
Nuclei
it
is
is
fixed and electrons are moving.
okay. So in Coulomb potential, the electrons are moving, but in
Yeah.
Hartree potential, the electrons are not moving.
Okay, so there is two things. In Hartree potential, actually, we are considering only electrons.
Yes.
So first, there are two things. This is our nuclei, and around this there are so many electrons. This is another nuclei, and basically, say one electron is here and another electron is here, so they are interacting with each other. So that means this this will take care the Hartree potential actually, this one, and nuclei are assumed to be fixed, right? This is for the Hartree potential. But when we talk about the Coulomb potential, basically the pseudo potential approach or the full potential approach, here we are considering only one atom actually isolatedly. That's how that electron say. And now I am looking at the so many nuclei together, and nuclei are freezed, and where I am considering only the interaction among the electrons. But in this case, what we will assume that say it is a nuclei and electrons are revolving around it, right? So here what we will assume that say mainly contribution which electrons are contributing, only valence electrons are contributing for it. So how these valence electrons are interacting with this, because they have to interact. So here we will assume that these valence electrons are sitting under the collective influence of this nucleus and core electrons, right? So that's what we will assume in the pseudo potential approach.
So actually, in Hartree potential, what is the meaning of this fixed electron? Because you are considering electron of whole system and interaction
Again,
between them.
it's okay. Fixed electron means typically we cannot call it as fixed, but we can say that they are the free electrons, a type of free electrons. In Hartree, what we do in the Hartree approximation, if I come back to there.
Is it so that in case of Hartree approximation, it is a case of hydrogen-like atoms where single electron is there? Can we say like that or no?
No. Actually, what Hartree suggested, say, if I have to deal with the multi-electron systems, so psi1 is related to one electron, psi2 is related to another electron, and psi3 is suppose related to another electron. So what Hartree assumed that these electrons are interacting with each other, but we assume these as a free electrons. So then total wave function can be written as the product of individual electrons wave function. But they are not free. So then they assumed that they are under some effective potential, means they are free, but they are under the effect of some effective potential. Because electrons are not typically free. But to mathematically to treat this problem, Hartree did this. Actually, this is all about it. Here Hartree is not talking about the nuclei.
Okay, can we assume like that, sir, in this case, that as a first approximation, it is considered to be a free electron, but to move
Yeah.
closer towards the actual situation, we make a second approximation that it is not free, but there is another potential which we consider to be the
Yeah.
more towards Coulombic potential on nucleus. Is it like that?
Yeah, it's like that.
Okay, okay. Thank you, sir.
So is this clear now?
Yes, sir.
Okay. Okay. Then there is another approximation to take care exchange and correlation. So this approximation uses only the local density to define the approximate exchange correlation, and so it is called the local density. But it's not a local density because position to position this density may vary. So for that we will use generalized gradient approximation. And if you go for the more accuracy, people will use hybrid functional or the meta GGA. And if your systems are semiconducting, and if you want to do some better calculations like catalysis, photocatalysis, like, then you must estimate the band gap in a better manner. For that, you have to move towards the hybrid functionals. And this is a simple algorithm for solving the Kohn-Sham equations. And it is self-consistent mode. I think no need to talk about it because our codes will definitely take care that this. Yeah. Now I am coming to the practical implementation of density functional theory. Now there are various computational codes available. Some are the open source, some are the proprietary codes to perform
So
the density.
I
Yeah.
have one doubt. This regarding that earlier slide, LDA and GGA. Please
Uh,
go on that. So in local density approximation, we are. It means we are considering uniform density. You are talking about.
Uniform density. It's a free electron gas, like.
Okay, and in GGA we are considering it is varying basically location to
Varying
location.
position, location to location.
Okay, so in that case, we will consider the gradient of density.
Yeah.
Okay, and one more thing, this you have written in this for more accuracy, one can use a hybrid functional or
Hybrid
meta
function.
GGA.
Meta GG. Yeah.
So can you just tell about them in one line, one or two lines about them?
Okay, I will tell. I will tell. Hybrid functional, basically, in hybrid functional, we will take a mix of both LD and GGA. So few percent of LDA is used and few percent of GGA is used. That's what we do in the hybrid functional, typically.
Okay, sir.
And in meta GGA, we are not taking the only first order derivative as we are not taking del and R. It is, so that means energy is a functional of not typically nr. This is a local density approximation, and in GGA energy is basically functional of nr. Sorry, it should be in the square bracket, comma del nr. But when we go to the meta GGA, then it is del nr. This is one thing, and del square nr, or you can take higher differentials of, then this is known as meta GG.
So in hybrid functional, how we will write ENR and delta NR, and how we will define the percentage of this LDA and GGA?
For this, different functionals have people worked. For example, HSE06 is a functional, and PBE0 is also there, and B3LYP. These are the different functionals. Different functionals have different mixing parameters.
Okay, sir.
Yeah.
Actually, one more question.
Yeah.
In hybrid functional, you just told me this. They are the algorithm they use like that. But as you just written ENR and ENR comma grade NR
Yeah.
for clearly for GGA and LDA, then how we can mix? So in terms of basically some
Say
intuitive.
suppose 20% you can take LDA and you can take 80% GGA.
Okay,
It's like that.
okay,
So different जो flavors, there are different flavors as I told you. It is PPE0, it is HSC06, or it is B3LYP. Uh, the people who developed these functionals, they have mentioned in their search papers that how much they have. Even few Hartree is also Hartree potential is also contributing there. LDA is also there, and GG is also there. That's what they do actually. And they definitely improve the results. Even GGA will underestimate the energy band gap, but if you do a hybrid functional, that will really improves the things. But it's a very costly calculation when we do the hybrid calculations.
I think in LDA this band gap becomes 0. It is like that. I think.
No. Actually, LDA gives good results for sodium, potassium, like, and for rest of the system, it will not give us a better result.
Okay.
Because sodium, potassium, they are like free electron gas type like systems. So for that, it will work very well. But rest of the it will not work very well.
Sir,
So it
for
depends
vanadium,
system to system on which system which will work. It is like that.
Actually, GGA, but for everything very well.
Okay.
Yeah, so better you should use GGA, and in GGA there are different exchange correlation flavors are available.
Okay.
So you can try with different flavors. Say PBE is also there, PBSOL is there, PLYP is also there. Which exchange correlation functional suits your system, that you can choose. Means you
Okay.
can try with different flavors.
Thanks.
Okay.
And
sir,
okay.
Yeah.
sir, for vanadium, which will be more suitable, GGA or hybrid?
When actually GGA is better, and for if you want to go for the hybrid functional, if you're doing optical calculations, or if you are doing some uh, photocatalytic properties, then you can go for hybrid functionals. Otherwise, if your system is a metallic, then GGA is better, because the cost of computation is very high for hybrid functionals.
Sir, so we will get more accurate results with respect to experimental results of band gap, right, sir?
Actually,
When we use.
when we use hybrid functional, then it gives us better results for semiconducting systems.
Okay, sir.
Yeah. So now I proceed further. Okay. So there are various types of computational codes, like depending upon that how atomic electrons are treated, they're termed as the full potential codes. So full potential Wien 2K is also there. L code is also there. Then pseudo potential based codes are Siesta and Castep. And then atomic sphere approximation based codes ASASPRKKR. And there is another classification on the basis of which we can classify our codes. That how electrons are treated means what type of basis set we are using to expand the wave function. Then first type of codes are the plane wave codes, like quantum espresso, even it is also there, BASP is there, CASTEP is there. Then augmented plane wave codes are also there, like ELK is there, Win2K is there, exciting is there. Then local atomic orbitals as a basis set, if we consider that as a to treat the electron, then Siesta is there, FPLO is there. These are the this is a very brief classification of codes. Means one is the how we take the potential, it's a potential based codes, and another is the how we treat the electron, then that is
So one is either the full potential or the pseudo potential based codes, and another is the basically it's plane wave based codes or the basis set atomic orbital based codes. This is a very brief classification. And I talked about that what is the pseudo potential. Okay.
So please, whatever on what basis you did the classification, you just explain what is full, when we call full potential, when we call pseudo potential, atomic sphere,
Okay.
approximation,
Okay.
plane wave, augmented, or these things. Please explain
Okay.
in brief.
Okay, I will tell you about the full potential and the pseudo potential based codes because I'm not working on this, so I'm silent about it. I will remain, and then this is augmented and plane wave. They are related to each other almost, and then third one is the atomic orbital based codes. So let me look at the say this is a nuclei and electrons are there. Say 4 electrons are there and 2 electrons are there, and like this 8 electrons are there and 8 electrons remains here. So in the full potential codes we are considering that there is a nuclei, and under the effect these electrons are sitting, so that means we are considering every electron. We are considering these electrons are also, we are considering these electrons and these electrons, all electrons are considering. That means here under the influence of nuclei these all electrons are sitting, and they are also influenced by these electrons, because the electrons which are sitting here they are also influenced by these electrons, and the electrons which are sitting here they are also influenced by these electrons. So this is the all electron, or we can say that full potential based codes, right? And another is thing is about the full potential based codes. So what do we do in the full potential based codes, sorry, pseudo potential based codes? Actually if I try to or go back to our beginning of beginning lectures of the chemistry, then we say that uh, whole of the chemistry is around about the valence electrons. So what we do, say this is the nucleus and say these are the core electrons. So how, what do we assume that say these are the core these are the valence electrons, and this this part which I shaded, this part is basically, this is basically nucleus plus core. So what do we assume, that valence electron sitting under the collective influence of the nucleus and the core. So that means here we have to consider only the valence electrons and in our calculation. So that means number of electrons in our calculation has been reduced. So this actually speed up our calculations. But rather than this, if we take every electron under consideration, then this will affect our calculation. This will cost a large computational cost.
So can we
So
assume that full potential is like a many body problem and pseudo potential is like bringing it down to two body problem? Can we say like that?
we cannot say that it's a two-body problem, because here under this influence, 3 electrons maybe, 4 may be there,
Yes,
but
yes, of
it,
course.
yeah, yeah. So
Means
basically, it's basically to treat a lesser number of electrons.
okay,
Basically, our purpose is
it's
because
like
if we
simplifying the problem.
yeah,
And between
simplifying the
valence
problem.
and non-valence, all potentials, nucleus
Yeah,
plus.
yeah.
Okay, thank you.
And even we can, in pseudo potential we can do core corrections also. It's a separate lecture of pseudo potential where you can learn that how core corrections people made. So if you generate your own pseudo potential, then you have to make the core correction, then your results are much more better. core corrections means because core correction significantly affect the behavior of the valence electrons. For that we do core corrections. So now this point is clear regarding full potential and this.
So it means when we are just calculating such properties that are affected by the valence electron, then we have to consider the pseudo potential.
Yeah.
And it will save our time also.
Yeah. If you want to do calculations with the say full potential code, then it require a huge machines and the last time will be required.
Yes.
But you have to in full potential codes need not to worry about what is your potential. It will these codes will automatically take care of the things. But when you have to work with the siesta like codes or the castep like codes, you have to know your pseudo potential. Sometimes you have to generate your own pseudo potentials.
Yes.
Yeah. And then another thing is the plane wave uh, and the atomic orbital based codes. So say this is electron, and electron is basically represented like this wave function. This wave function, this is basically wave packet. So how to treat this electron wave packet? And if I take its say it is a psi, and if I go to the psi star psi, then that it should be like this. So typically its behavior is like this. So its behavior is like this. So मुझे ये behavior I want to represent this behavior. So what are the different ways to show this behavior actually? So in plane wave based codes, basically when so many wave functions of different amplitudes of frequency, they are added together like this. Then these type of different wave function they are added together, then they gives us like this. So it is basically a wave packet like behavior. So these all are the plane wave. So that means when we add so many like waves, so that means in plane wave based codes we have to add so many sinusoidal waves together, and their superposition tells us about the, or their linear combination tells us about the electronic behavior. And another important thing is that in the atomic orbital based codes, say all of us are familiar with the s orbital. Sorry, 1s orbital, its shape is like this, 2s orbital is like this. So this is the radial part of, this is the radial wave function. So when we treat this as a way to represent the electron, then such type of codes are known as numerical atomic, or means atomic orbital based codes, and that's what siesta will do. Now I am treating electron as it is, but in the plane wave codes there is a problem with that, that we are treating the plane wave based, but there is a problem with the plane wave based codes, because plane wave based codes are uh, they take more computational cost. Reason for that, suppose there is a simulation box. There's a large simulation box I'm considering, and in large simulation box only two hydrogen atoms are sitting. One hydrogen atom is there and another is here. But if we want to do calculation with the plane wave based codes, then what will happen? We have to consider the large number of plane waves, even for vacuum. Whenever there is no wave, whenever there is no like atom is there, but this is my simulation box. So for vacuum, you have to consider the plane waves also. So that increase the computational cost very large, right? Now the point is clear.
Actually, what is this augmented plane wave?
Augmented, it's also like plane wave based codes. It's a little bit different form. I'm not exactly, I don't know exactly what it means, but this is basically like a plane wave.
So, in short, we can say this localized atomic orbital means we are taking orbital as it is, but in plane wave we are just assuming
Now
this basically
plane
approximating the
waves,
orbital with the combination of the plane wave,
yeah. But
right?
if you want to do calculation for bulk materials,
Hello,
then plane wave code. Hello, yeah,
hello.
yeah, you are right.
So you were saying something, if you
Hello.
want to do calculations for bulk material,
Yeah,
then
yeah. If
Sir,
you
your
want to do,
voice is breaking actually.
others are. I'm audible properly for
yes,
others.
you are already audible
Okay.
properly for at
Well,
least.
there is a problem at your end, I think so.
So you were saying something that if you want to do
Yeah,
calculation
I'm
for
saying
bulk
if you
material,
want to do calculation for bulk materials, then plane wave codes are good and full potential codes are maybe good. But if you want to switch from bulk materials to the two-dimensional materials or one-dimensional materials, even zero-dimensional materials, then siesta means localized atomic orbital based codes are better.
So actually, this whatever this bulk in the bulk case we have the periodic system. So in that case, we have to use this plane wave kind of thing.
Yeah, plane wave. Actually, periodic is everything is periodic actually computationally. But in that case, we have to take a large box so that interaction will be least. I will tell you that if we got a time that during the hands-on sessions, that how periodicity can be taken care.
Okay.
Yeah. So even there is how much time do I have?
So you can continue.
I think this is large one. It will take more time, but as on my behalf, actually, the a brief introduction is complete right now. Actually,
Okay, then sir,
so
you
in the
can
lab
start.
session,
Yeah, you can start with the
yeah.
lab session, sir.
Okay, so can I take a little break? 10 minutes,
Uh,
5 to 10
okay, fine.
minutes break.
Not 10
Yeah.
minutes, 5 minutes.
Okay,
Sorry, sir.
I will 5 minutes. I will
Okay,
continue.
okay.
Okay. Any query right now?
Sir, it will be given. There will be another session for you.
Oh, okay.
After hands-on training, there is an interactive session.
Okay.
There you can discuss about
Yeah.
the.
Okay. So I will meet after 10 minutes and then we will take a hands-on session and rest of the things can be taken care there.
Okay.
So thank you.
So all the participants are requested to take break for 10 minutes. After 10 minutes, we will start the hands-on training. So till then, please join us. Okay, sir, you can start it. Arun, sir, you can start.
Yeah. Okay.
We are waiting for the recording. So recorded now, you
Yeah.
can start.
So my screen is visible.
Not yet, sir. Please share it. Yeah, it's
Yeah,
fine. It's
visible.
visible, sir.
Okay. So the important thing is that
Please wait, sir. Please, sir.
visual
Please,
because
sir,
now I'm
excuse
talking
me,
about
sir.
this. Yeah.
Excuse me. So all the audience participants, is the screen is visible to you? Please respond it once, and if it is visible, please open your software, which the committee has sent you some link to install some software. So if it is installed, please open it and do it with Arun, sir. Okay, sir, you can start.
Okay. So if you are beginner, that means you have to install the Linux operating system on your machines. One thing is that. So I have shared with the organizers that how to dual boot your machines. Sometimes people will virtually install Linux along with Windows, but virtually there is a problem. Actually, Windows is also using your resources, and Linux is also using your resources, and then you cannot do calculations fast. It's one thing which we have to keep in mind. So you have to install the Linux along with Windows. So first of all, you have to install the window, and you have to allocate or the free some space, and that free some space can be utilized to install the Linux. And you have to install the uh, or you have to partition the hard disk properly, and that you have to keep in mind. Then once Linux is there on your machines, then uh, let us now first of all go to the back page from where you can download CS star. So I'm just going to the CS star back page, or you can download it from GitLab also. Say taking little more time. You can go to the V4.1.5. It is a stable release. 5.0 is not stable release. There are some bugs or certain issues right now, but better you should go for V4.1.5. And you go to here code and click on tar gz, and it will be downloaded in few bandwidth. Let me comfortable you with the commands. Say
There is one question in the box that yes, download
right now we are in the
Hello, sir. Am I audible?
Actually, there is a network problem from your side.
Okay.
home direct. Am I audible now?
Yes, yes, it's audible.
Okay.
So please start from the beginning. Some
Yeah,
participants are asking that they do not know how to download the program.
okay, right. So basically,
So
let me
please
first
share
of
the
all
screen
share
first.
my screen. Yeah.
Okay, fine. Thank you, sir.
So my screen is visible.
Yes, sir, it's visible.
Yes, sir.
Yeah. Okay. So v4.1.5 Siesta version you have to download. So I downloaded it from here. So it is there in the downloads. If you are beginners, so this is basically Siesta. I copied it from here, and I have made a folder on my machine, say in the documents. Yeah, let me do it on the home also. It's typical in the home. Uh, I pasted it here and I unzipped it. I extracted it here. So this is Siesta, right? I just right clicked on that on it and then open a terminal. So this is my present working directory, right? So I am basically now inside the Siesta code. So we have to install it. So you have to simply go to the obj directory. CD means change directory, and I am going inside a directory. It is a obj directory. I just copied it. You can read me file to install it, but I know the steps. So what you should do? You simply give a command sh double dot slash means I am coming out of this obj directory and going inside, going to get into some other directory, src, this directory. I go inside it and I put a tab, then it shows me different directories inside it. Means src, inside it these files are there. This the files with slash, these are the directories and these are the files simply. So basically I want to run this script here, obj setup.sh. Means I am inside a obj directory, and from here I am going outside obj directory and going inside the src, and then I run a script, and script can be run with the help of a sh command. That's it. And now it says that compilation setup done, and these are the files: gfortran.make, intel.make, document template.make. So that means before installing Siesta, your machine must have some compiler. Say Fortran is also there on your machine. M4 package should also be there. So basically, before moving towards further, so you have to install few packages which are needed. Say sudo apt-get install. Say M4 is one package which is needed. Okay. GNU plot is also needed. First of all, G++ is needed. GCC is needed. Gfortran is needed. And then uh, VIM is also needed. Then M4 is also needed. These are the certain package which are needed. And then GNU plot. These are the few packages which are needed, right? You simply write down their need. apt-get install, it helps to install automatically in the Ubuntu based systems or Mint based systems. You simply enter, and it will require a super user password. That means these all are installed. So on my systems, all the packages are installed actually.
So actually, if we want to work with this software, then we have to use this Linux. We can use in Windows.
You can use the Linux environment actually.
Sorry, for this Siesta software.
Siesta software, right?
So can we use the software in Windows also?
No, we cannot use Windows.
Okay.
I have shared some videos. Actually, in those videos, you can dual boot your machines also.
Okay.
I share two videos. Yeah, you can either upgrade your machine or you can install Linux along with the Windows operating
Okay.
system.
Okay, sir.
So that means when I give that command, basically I have given this command and it worked for me. So it says that remember to copy an arc.make file into the directory. And what are the templates? These are the few templates. Say gfortron.make is also one template, and intel.make. If your compiler is a Intel compiler, there are different compilers of Fortran. Intel compiler is also there, gfortran compiler is also there, MPI compiler is also there. So if your machine has a gfortran as a compiler for Fortran, then you have simply copy gfortran.make as a arc.make file. Means I copied gfortran.make file and written it with a new name, that is arc.make. Say I did this one. So earlier arc.make file is not there here, but now it is there. So simply you have to give a make here, and then it will work for you. So it will take few say 1 minute or 2 minutes to compile siesta properly, and if everything is there, then it will easily compile. On my machine it is already compiled, so you will try with this how it will compile. And in the meantime, uh, I have I go to you can go to my web page arunphy.org. This is my web page. You go to here. Let me show you with the address of my web page.
Sir, I have shared it.
Okay, you have shared it. That's it. So this is my web page, and on my web page I have made a workshop, and under workshop you can go to the AIP workshop, and in AIP workshop there is a folder named Siesta examples, so you can download this folder in the meantime on your machines, because there are certain scripts or certain examples which will work for us. So in the meantime, it gives some error, right? There is a type mismatch between actual argument at one or these two, right? So for that, what you should do, you can open arc.make file, and in arc.make file, at this line you have to make some changes. On my website I have also written it. Let me go to there and share. There is a e-resources queries of learners or students of under this queries of yeah. So this type of error is there. So basically what you have to do, you have to replace this line with this.
Sir, I have one query. I am not able
Yeah.
to install Linux at my machine.
Okay.
So Is there any way out, or the only way out is I should uh, watch whatever is going on at this meeting, and afterwards I get some expert to install Linux, and then I do some practice or what you are
Actually,
doing.
I have made so many videos of actually band structure calculations, periodicity, so on my YouTube channel.
Yes, sir.
So
Sir,
that may help
actually,
you.
I just want to interrupt it. Sorry for interruption. Basically, sir, you need to install the Linux first. Then after that, you will be available the recording of this video in our YouTube channel.
Okay, very good.
Okay.
Yeah.
Then not only that, you can also go to the Arun sir web page afterwards, and you can do all the things.
Okay.
Even it's a little bit difficult to sum up everything in one hands-on session. So
Yes,
basically,
sir.
so, so actually, I have made little small videos regarding the siesta, and various examples are there on my even web page. You can go, or even they are also recording, so you can go to there also. So basically, this changes I have made into this arc.make file. So once it is there with this, I have saved it, and then again make it, and in few minutes it will be there. So when we run siesta, we need two things. So in the meantime, when it will run, in the meantime, let me talk about few things. Actually, when we run siesta, then we need input file. Sorry, we need input file, and then we need PSF file. So what is a PSF file? It is basically a pseudo potential file of the atomic species. For example, I want to study sodium chloride structure. So when I want to study sodium chloride structure, I need a pseudo potential of sodium and I need a pseudo potential of chlorine. So that means I need a file na.psf and I need a file cl.psf. These are two files which are needed. One thing is there, and another file is the input file. And what this input file? It contains structural information. And what type of exchange correlation we are using. And various other parameters which are needed. See, block for band structure and block for density of states. These things are there in it. So that means FDF file means free data format file is needed, and another is PSF file is also needed. You can generate your own pseudo potential files also. There is atom code inside. There is atom code. You can download that and install that code, and you can generate your own pseudo potential. Another, if you are not generating your own pseudo potential, then there are different databases are available on the internet. Using those databases, you can uh, download PSF files of the different atomic species from there, and you have to make your own FDF file. So let me briefly talk about, say, so the siesta is installed now because it gives no error. Say ls means list, si star means, say, siesta is yes, siesta executable bundle. It's there with us. So what you should do, you should copy the siesta executable from here. Copy siesta from here, usr local bin. This is the important command. So it says permission denied, so you have to give a sudo command, sudo cp siesta usr local bin. So it is there with us. So siesta is installed, and after siesta installation, you have to go to the utils, and in utils you have to build all, because there is a bands utility, and there are so many other utilities, say denture for the charge density analysis, bands for the band structure analysis. Then after that there is another, that is Vibra for Funon calculations. You can use this tool. After this there is Contrib. In Contrib there is another very important tools. Yeah, Apostnico cd Apostnico. It contains so many scripts. So for to install all these packages, what you should do, you should simply use this script, build all.sh /build all.sh. You have to use this script for this, and it will compile every package for you. I have already compiled, that's why I'm not doing this here. So you have to do /build all.sh. Okay, let me do it here. Say it will compile so many packages for me, right? So I have shared with you that you have to download the folder from my web page. Have you downloaded that? Have you downloaded it?
Yes, sir. Zip file is downloaded.
Okay, so unzip that, because I am also doing the same text task whatever I'm sharing with you. So I go to that let me go to that directory. Yeah, it is AIP, and inside it there are certain examples. So first of all, let me, yeah, let us start with the gold example first of all. Hmm, okay, let me go to the inside it. Here there is folder named files, right? And inside files you have to go to gold. So go to, say, go to inside FCC. So what I did, I go to the AIP workshop folder, sub workshop folder is there, then go to the files, then gold, and after that I go inside the FCC. And in FCC, now let me understand this FDA file. Say in this folder you got a gold.fdf, one FDA file, and another is the gold au.psf. This is the pseudo potential file. So let me open this gold.fdf first of all. Yeah, I just opened it, right? So let me briefly talk about every parameter which is there with us. So it is our system level. AU is there, number of atoms, this is one atom, number of species one, because I am taking one atom, and that one atom is repeating itself in all the directions so that it is behaving like a bulk material. And this is the atomic number of gold, this is its species level. So means the name which I have written here, same should be here, dot psf, right? So this is the information of one atom. Then these are the lattice vectors, LATT. Actual lattice constant is 4.009, but I have make it as a variable here. I will tell you that why I'm taking it as a variable. And there is only one atom which is there, right? So FCC hai, it is FCC, and I am taking one atom. Why I am taking one atom? Because I am taking it in the primitive mode. Let me draw a diagram first of all. Am I audible?
Yes, sir. It's audible.
Okay. Yeah. So let me talk about that. How why I am taking only one atom. So if you try to look at the FCC, then what is there? One atom is at the corner, and four atoms are at the sorry, one atom at the corner, and three atoms at the faces, at the face center. So this is one atom. Say one atom is sitting here. I am marking it with a different color. One atom is sitting here, and another atom is sitting here, and another atom is sitting here. So this is FCC, but it's what is the primitive of FCC? Primitive cell of FCC. So basically, when I join this with this, and I am joining with this, and all are equally distant. So that means I have got a three lattice vectors. Earlier in this structure, our lattice vectors are this. One vector is this, another is this. So it is 1 0 0 0 1 0 0 0 1. These are the lattice vectors. But when I'm taking primitive, in that case, my lattice vectors are this one. One vector is this, another vector is this, and another vector is this. And if I take these three vectors, then the cell which I'm getting here, this cell is basically primitive. So if I try to look at it, this contains only one atom. But this red colored is containing four atoms per unit cell. So this is the primitive cell which I am taking. So that means it contains only one atom. And what are its lattice vectors? See, if I try to look at this lattice vector, then say it is x-axis. Sorry, it is x-axis, it is y-axis, and it is z-axis. So it is in the z plane. This vector. So its coordinates are what? 0.5, 0.0 and 0.5. And what about it? It is in the xy plane. So its coordinates are 0.5, 0.5, 0.0, and it is in the yz plane. So it is 0.0, 0.5, 0.5. So these are the lattice vectors which I am getting. So lattice vectors kiske liye hain? These are for the FCC. So that's what I have taken. That's what I have taken here, right? And I am taking only one atom. It is basically in the primitive mode, right? So this is one thing which we have to keep in mind. Then I talk about basis sets. So basically, when you are doing calculation, then PO basis type is split, DZP double zeta polarized. Basically, these are the numerical atomic orbitals, as I talked about in the morning lecture. And this is the cutoff for what we call basis set. numerical atomic orbital basis set. This energy defines its cutoff. So 20 MeV is sufficient. Means when you do calculation, better you use MeV to 50 MeV, any value. So 20 MeV gives us a better results. Then these are the exchange correlation type flavors. So say first is the GGA. Which flavor of GGA you are using? Somebody asked me the type of flavors. So PBE is also there, PBESOL is there, RPBE is also there. There are so many types of flavors are also available. So if you want to do spin polarized calculations, means if you want to see whether magnetism is there or not, then you have to use the spin polarized flag true. Then self-consistent iterations 2000 is sufficient, but if your calculation will not converge, then you have to change this value. SCF iterations, you can change this to 2000 to 4000, but if it converges earlier, then it's fine. Then DM mixing weight by default value is 0.25, but 0.10 is good value. But if your calculation is not converging, then you can change this parameter up to 0.01 or 0.005 कर सकते हो. You can take it as 001. But if it is converging, then 0.10 is a sufficient value and very good value. Then another parameter is the mesh cutoff. Mesh cutoff 300 Rydberg is sufficient. If you take higher value, computation cost will be large, and if you take smaller value, then your results may vary.
Hello, sir.
Yeah.
I want to know some terms in that. What is this mass cutoff? And first of all, I want to know this PBE. So, can you introduce what is this PBE? What happens inside this? What type of
Yeah.
exchange correlation function is this?
It is basically GGA I'm using here. It is PBE means it is GGA.
Okay.
It's a GGA flavor. GGA has different flavors. PBE is also another is means different people try different type of exchange correlation function they have devised. If you go to the manual of CST, you will get a large number of flavors. Say RPBE is also there, PBESOL is also there. But it's different type of functionals. Mostly
So,
people use
how they
PBE or
built
PBES.
this functional PBE, all these things? So, it is written there. What they have
Yeah,
come
it is written.
from
Yeah,
in that.
yeah.
And this, what is this mixing weight 0.1 you are taking?
Okay. DM mixing weight actually it will mix the density matrix. Actually, what when we do calculation, it will mix the earlier result and the new one. So when we mix, and it must converge to a particular value actually.
So it means when we are doing the self-consistent field calculation, in that case, it will try different solutions. So it will
Yeah,
mix
different solutions.
something
And
from the
when it
previous solution. It is like that.
previous solution, yeah, it's like that.
So just scroll down one more term I want to know.
It's a mesh cutoff, right?
Yes.
This is also another convergence parameter. Actually, what will happen? mm, uh, Let me finish first of all this. Let me show you one result, and then after that, I think I will talk about this mesh cutoff and so many other
And
parameters. Right?
occupation function means we are taking electrons, so that's why we are taking Fermi drag, right?
Fermi track, yeah. Another features are also available there. Even you can go to the manual, but this gives us better results. Occupation
Yes.
function, and these are the high symmetry points for reciprocal lattice vectors. Means this is the block for the uh, band structure calculation when you want to do band structure calculation. So in any code, you have to mention these high symmetry points: gamma, L, K, W, X, U, gamma. These are the high symmetry points. So these are the flags for this, and this is the uh, grid K grid for doing integration in the reciprocal space. Because when we do calculation and we got a real space, convert that into reciprocal space, and when we do integration in the reciprocal space, then we will get the band structure, right? So this grid basically represents the grid for doing integration in the reciprocal space.
So in this high symmetry points, these are the coordinate of points in the reciprocal space last in middle columns. And in first column, what is this 150, 50, all these
Okay,
things?
150, 50. Actually, 0 to first point is the 1. Gamma is at the 1 point. And after gamma to L, I am taking 50 data points. And
Okay.
L to K, I am again taking again 50 points. And LK to W, again, I am taking 50 more points.
So these are
That
the
means
number
how
of
many
points
number of points which we
between
get.
gamma and L and K, all these
Uh-huh.
things. Okay.
Yeah. You can change these numbers also. But if you take a less number of points, then rather than smooth graphs, you will get sharp lines.
Yes.
So sufficient large number of points should be there, so that you will get a smooth curve. And this is for the density of state block, because I have made these FDF files. Actually, these are the standard parameters which gives us a better results. Even by default, you will get those parameters which will converge calculations fast, but don't give a reliable results. And this is the Mulliken population. This gives us the charge if we want to do charge analysis. And then there is a MD type of run, conjugate gradient is its meaning. So when you are optimizing structure, that means number of CG steps should be large, but means 0. And what you want to relax the structure items, then you have this number should be large. It may be 1,000, it may be 2,000. And these are the flags for the optical calculation, but I'm not talking about these here. And these are the flags for denture. I have commented all these parameters right now. Optical calculation, I have also commented it here. And for the charge density analysis, there is a denture tool which uh, gives us charge density analysis, but I have also commented all these. Means this is up to here only, right?
So
Okay,
this
so
projected density of a state means it is integrated over K. It is like that.
yeah, it's no, yeah, it's like that, but it's a density of states. It's from
Simply
the K
density of a
space.
state means EK in EK diagram. If we integrate over K for
Huh.
one omega value, then it gives the density of its state. It is like that.
Yeah.
Same thing.
Yeah, it's like that. Yeah.
Okay.
Okay. So this is a brief introduction to the FDF file. So what I did, let me go back to in yeah. Now the thing is that what should be the our lattice constant? How do we come to know that? Because in FDF I have mentioned, in case of lattice constant, I have mentioned LATT, right? And what is this LATT? Because actual lattice constant is 4.09 for gold in the FCC lattice. So I again opening yeah, this is it. So basically what do we do? In your FDF you can make changes. Say we can start with the 3.5 to say 15.0 in a step of 0.1. So that means what I'm doing, I am changing that LATT. First of all, I have taken that 3.5, then 3.6, 3.7, and so on up to 15.0 in small steps, right? So gold.fdf will become a new FDF au.I. And what is I? I is taken from this. So first of all, I is 3.5. So what it will do, in gold.fdf, otherwise you have to do all these things manually. In gold.fdf, it will replace LATT with I, and the first value of I is 3.5, and it will make a new FDF file, au.I. I means 3.5.fdf. It gives us a new FDF file, and this is a command to run siesta. Actually, I have made it as a siesta_par because I have installed siesta in parallel mode. That's why I am simply. Otherwise, you can simply do it by putting siesta. So it is siesta command. I make some changes into it. Then au.I, automatically it will run this FDF file and make a new output file. And in the last, I will grep the total energy. Right? So this is a way. So what will you do? You simply save it, and then it is a script. Let me check its names. Just a minute. Yeah. ls. So ebs_lad.sh, you have to make it executable. So to make it executable, chmod plus x ebs_lad.sh, right? And it will become executable. Now you simply give a command /ebs_lad.sh. You have to give this command. See, it is doing calculation for us now. See here, it is making a file 3.5.fdf, and it is making output file 3.5.out file, and it will doing calculation for one position and then for the second position. So basically, what I did, is this clear up to now?
Yes, sir.
Okay. So it did calculation for one, and then it is doing for the next position also. See here, it is doing calculation for the rest. 3.6 now it is doing. So if I go back, because I did these calculations, so I again go to the gold, and this is the FCC. I did all these calculations here. I started with the 3.80 and 3.90 and so on. And in the last, say if I go to the out file, say for example, I go to this out file. If I go to this out file, and in the last, you will get a total energy. In the last, you will get a total energy. This is the total energy, right? So we have to have a look at this total energy, that how much is this total energy. So what I did, I grep there are so many out files, say ls*.out. There are so many out files which are formed there with us. So I basically grep, because there is a line total equal to, its T is capital, space equal to, and *.out means I'm going inside every out file, and ten.dat या 12.dat, जो भी आपने फाइल का नाम रखना, whatever you want to put, you can. So it is a 12.dat. So what I did, I put energy information and put it inside the 12.dat. So that means there is a file gedit 12.dat. So this is the information which is there with us, right? So In the gedit, I opened it, give a command, Control H. Then you have to remove every line, AU dot, you have to remove it. So I removed it. Then I have to remove dot out C star, this also. So I copied it because this is not needed, because I need a dat file. Yeah. So replace all, then total is also not needed there. So this is how. Now see the order. It is 3.858,690, then 4000. It's fine. I think it is in the increasing order. Everything will be in the increasing order. But yeah, in the last, it is this one, 4.01. Because once I got the rough estimate, then I fine tune the result. So 4.1 to 4. Yeah, D5. So this is my information, right? So I arranged it in order. Here I have fine tuned the data and then I saved it. Now I want to plot it. You can use GNU plot, or you can use any other tool. You can use Origin, you can go to the Excel, or you can use XM Grace. So plot, it is 12 dot dat, it is WLP. This is the data which we are getting. See, so this is the point at which we are getting the minima. So what we did actually, for the different lattice constants, we try to solve the Schrodinger wave equation. We try to solve the Schrodinger wave equation. Say, this is one value, this is another value. Say the point at which we are getting minima, right? So this is the lattice constant. And if I go to here, then we see that energy converges to a particular value. Here keep on increasing, and then it converges to a particular value. So this is known as cohesive energy. The difference is known as cohesive energy. The plot which I shown in the beginning in my morning slide. So this is the cohesive energy. This is the lattice constant which we are getting here. It's a very simple thing. And say I did the calculations. Calculation is running. Say, so we have calculation slide. It's running. See, it's about to complete.
Sir, in various material science data files, we have the lattice constant. Is it?
Yeah, it is given.
It is given. So whether it is done with the which theory or it is experimental, how to know?
Experimentally, some databases show experimental results, and on some databases they did calculations with these DFT codes also actually.
And as we discussed, there are many different theories we discussed. Like we have LDA, we have GGA. So
Yeah,
which one? Suppose I use two of them, and will they give me different results for lattice
LD and
constant?
GGA will gives us the different results. So actually, GGA gives us better results
Okay. And
if we
sir,
if we compare.
yes, and here we have changed the lattice constant. But what are the other
Yeah,
parameters which can be changed to all the equation?
uh, it's a K mesh. We have to take care that it is the energy shift we have to take care, and it is the energy shift is there, mesh cutoff is there, K grid points which we have to change. Actually, these are decided by the energy convergence. Actually, let me take one example
What
to
is
you.
K here? Is it the
So
wave vector?
K is the wave vector.
Okay, okay.
Say suppose I am doing a integration in the reciprocal space. So when I am doing integration, I am taking a 1 0 0 0 1 0 0 0 1. This is the 1 point. I will get the for 1 1 1 grid. I am getting a total energy E1 value, and then I2 2 2 2 2 इस तरह से I am doing it this. Actually, Siesta will put K mesh like this, and if you do this in the quantum espresso, then you will put 1 1 1 2 2 2 or 3 3 3. Actually, the way of giving these parameters it is different, but otherwise basic things will remain the same. Basic physics will not change. So when after this you will do this 3 3 3, and you will do 4 4 4 0 0 is also there, so and so on. So that means I am taking a 1 2 3 4 5 and 6 and so on. You will get the different values of energy. Actually, what will happen in the initial energy will fluctuate, and after some point 7 or 8 you will see energy converges to a particular value. And when energy converges to a particular value, then you have to choose that parameter. Similar thing will happen with the energy shift. Actually, in energy shift, what will happen? Energy keep on fluctuating, and then it converges to a lower value at around about 20 MeV. I made these lectures are also, these are also available on my YouTube channel, how these parameters are decided. So 20 MeV is decided in that way. And similarly, mesh cutoff, it is also decided in that way also. In mesh, say 50 and then 100 150 uh, 200 and so on, up to, you can do it up to 500. You can see the fluctuations, and then after 300, yeah, to 250, you will see energy converges to a particular value. So that means 300 mesh cutoff is a very means gives us a reliable results. If you take a larger mesh cutoff, then the results are good, but the computational cost is very large. So this is all about these different parameters. And there is also numerical atomic orbital basis at DZP gives us a better results. Means initial choice is single zeta, single zeta polarized, double polarized, triple zeta double polarized. So this result, this gives you better results. So do not go for higher values, because computation cost will become very high. And another interesting thing with Siesta is that you can do calculation either with your laptops also. You can do zero-dimensional simulations. You can do one-dimensional, two-dimensional, or three-dimensional systems. You can study either dimensionality. You can do with the Siesta code. This is the advantage of using this code, and it is open source code. Even I'm using since last 14 years. I'm using Siesta code. So this is the that's what yeah, yeah, it's done. So the calculation which is there, so I grab sorry, G added energy dot that is formed there, ये calculation the which we have run here right now. And see, so if I remove additional things, true latch is there. AU dot, I've just removed it, and then dot out extra, and this is total, and then plot it. Oh, blue plot. Energy dot dat WLP. Yeah, it's there. See, So that's what here we got the minima. It's around about 4 point. This value is probably 4.2. It's around about 4.2. So it is closer to the actual value, right? So the point at which you will get the minima, then you can do the band structure for that, band structure calculation for that. Means you have to put the file where you got the minima, or you can see if let me go to the energy dot dat, and if I try to look at it, say you are getting minima at 4.8. Yeah, you will get the minimum 4 point, no, 4.1, 4.2. See, you will get the minima at this point, 4.2. Even you can fine tune this calculation also. So I am taking 4.2. So I will again took this FDF with the 4.2. I make a directory final here, and I copied file au dot 04.2.fdf to the directory which I made final, and I just copied au.psf there. See, I'm go to the final. Yeah, so it contains two files. Means FDF corresponding to minima and then au.psf. Now again I go to au dot, see, it is 4.2. So corresponding to it, even you can do calculation for decimal for two decimal places, then that gives you better result. So I will run this, and these are the high symmetry point for FCC. So I just run it using siesta. It's a siesta command. Input file is, this is our input file, and this is tau dot out. Tau dot out. And I have shared with you, say job is done. So this is the dot bands file, right? This is the dot bands file. So if I go to the dot bands file, then it is like this. So this is the Fermi energy. These are the another parameters. And if I go to the last, so these are the positions of the high symmetry points: gamma, L, K, W, X, U, and the gamma. These are the high symmetry points. So you can plot the band structure either with the help of the XM grace or with the help of the GNU plot, and you can draw these lines also. So in the beginning, I told you that there are certain utilities because the time is short. So in utils, there is a bands. Inside bands, yeah, there is a GNU bands utility. So what you will do, you just copy this GNU bands utility from here to USR local bin. You just copied it there. It says permission denied, then gives a command sudo. Right now, what you will do, here we have completed the calculation. So you simply give a command GNU bands au dot bands t. I have to, because I cannot directly plot au dot bands, so I have to change its format to a new format so that I can plot it. So it is tu bands dot dat, or any name you want to write it as. So it is AUT bands.dat. So now the bands.dat file is formed with me. So it tells us Fermi energy, the value of the Fermi energy is there with us. It is K minimum, K maximum, and number of bands. It's for the one spin. Initial information is for the one spin, and and after that information is for the this spin 2. So means spin polarized band structure is there with me. And yeah, there is one more thing. Fermi energy is at where? Fermi energy is at uh, Fermi energy is minus 4.04. Some in mostly papers, what people do, they will put Fermi energy at 0. So for that, you have to shift the data. So for that, either you can shift manually, or there is a command in the GNU bands. Actually, if you give a command like this, GNU band space dash F space this one, then it automatically shifts the Fermi energy to 0, right? So I have shifted the Fermi energy to 0. Now what I will do, I have to plot this bands.dat file. So I am using XM Grace. So I go to the XM Grace and go to here plots. Even I have made a complete video where you can plot band structure and density of states along with, means how XM Grace will work, who are newer one. So it is the bands.dat file, and it's single data. I just plotted it and it gives me the band structure. So what I want to see the band structure near the Fermi energy. So I go to the here axis properties and go to the y-axis, and y-axis I want to see the band structure near the Fermi energy. So better I will change the, it is minus 5 to 5 in a step of 1. So this is the band structure which we are getting. ये हमारे पास band structure आ गया. It is the Fermi energy because I shifted it to this one. So have you completed up to this or not?
Sir, these codes are, new to us. So, do we have any kind of PDF or such thing so that we can have all commands uh, in front of us?
Actually, I have made small lectures from installation to convergence parameters. Say, let me go to YouTube. Just a minute. Yeah, it's my channel, and here I go to the playlist because see, because in one day or in 2 hour session it's a very difficult. So it's a, this is basically, just a minute, say here it's basically, I started with the simulation of hydrogen molecule, its pseudo generation, atom code installation, siesta installation, then predictive simulation of the bulk code using siesta, and these are the installation of necessary tools. Then there is a GDIS tool which is used to make a FDF file, and concept of primitive cell, and how do we choose the high symmetry points, then spin resolved band structure, then charge density, and pseudo potential generation, uh, carbon dioxide or water molecule simulation is there with us. And then there is a band and the density of states of the iron using GNU bands, FMP DOS utility, then atom code, pseudo potential data visualization. So these are the small videos which I made and made it available because in one day it's very difficult. Actually, if it should be 1 week, then we can cover so many things actually. Because when you are new one, then it sometimes it becomes very difficult in a short span. right?
Yes, sir.
Because here I can give you a little flavor of it, that how siesta will work. Because it's not like other codes where you simply put values and then everything will work for us. Uh, as BASP is a very good software, but it's a very costly. And for running a BASP, you require a very large machine. Similarly, Quantum Espresso, you require a large machine. But the advantage of siesta is that you can work at your remote places, and even with a laptop. Even I have sometimes hundred of atoms. I can run these simulations on my laptop also. Even you go to the research gate to look at my research papers. So I did all the calculations with the laptop only. Rarely I use the uh, big machines, HPC like machines. And you can even do calculations with the smaller dimensions materials also. And uh, and another important thing which I shared with you is that means is today, if you go to here, I shared with you, say if you go to this this, and see what I did. I shared with the BCC, FCC, and simple cubic, as I told you in the beginning lecture, uh, in the morning lecture. So see here, I tried with the simple cubic, FCC, and BCC, and I got these graphs, and I shared these folders with you as it is. I shared with you the files which are untouched, and in some folder I shared with you all these results, and see. And this is the band structure and how these high symmetry points are plotted, you can do. And as organizers asked me to give a some assignment for you, so silver is also like this. So as a assignment, I am giving you that you have to make a FDF file for silver also, or copper. Silver is better. So silver is similarly, you have to find the minima and the electronic band structure. These are the two things you have to do as a assignment. Because silver and gold, these look similar. So as a assignment, you have to take a silver atom and try to find out the minima, means estimate the lattice constant and the calculate the band structure. Even not density of states, right? And if you go to here another, if I did calculations for iron also. See, these are the systems for this iron also. And another thing which I want to share with you, if I go to there, it's gold. Yeah, inside gold there is a file, yeah, FCC. Inside FCC there is a final, there is a file, another file is XV. XV file is also found there. If you go to your final directory, yeah, this is the XV file. So there is a utility inside this, not here. Mm, yeah, I go to Siesta. In utils, cd contrib, Phosphiko. Yeah, it is there, right? These are the two utilities. One is the FMP DOS and another is the XV2XSF. So you have to put these utilities from here to the USR local bin, right? So once it is there in the USR local pin, so what you will do, XP to XSF, and it is asking for this AU. System level is AU. I just gives AU, and it says that file already exists, so I will overwrite it. So if I see here ls star dot x, so these are the sorry, clear, ls star dot xsf file is there with us. This is au.xsf. So there is another tool which you have to install. Installation of if it will work for you, then you give a command sudo apt dash get install xcrystal, then it will install the xcrystal, right? So I have already installed the xcrystal. So I open the xcrystal and go to the file and open a structure xsf file. It is the au.xsf file is there. This is it. I just opened it. So this is the gold structure which is there with us. See it. And if I go to the tools, you will get the K path selection. Just close it. Say this is the Brilliant zone of this gold. So high symmetry points are basically, these are the special points. Say the center of this Brilliant zone is known as the gamma point. Similarly, these are the another points. This is another high symmetry point. This is another high symmetry point. This is another high symmetry point. So how do we identify these high symmetry points? This is mentioned on the different uh, say structures. For example, let me go to the high symmetry point, because this is a very important thing. High symmetry points in the Brilliant zone. Say so gamma is basically center of Brilliant zone and simple cubic. M is the center of an edge. R is the corner point. X is the center of phase. So now let us come back to the FCC. So for FCC, say K is the middle of an edge joining two hexagonal faces. So this is the K point, because this is hexagonal face. This is also hexagonal face. So this is hexagonal face. So their middle is basically K point. And then what about L? L is the center of hexagonal face. This is hexagonal face. So this face is hexagonal. This face is also hexagonal. And this is basically square face. So these are the high symmetry points. Or ye kya hai? It is gamma 12. It is a high symmetry line. It is lambda. And gamma 2x, it is a high symmetry line. We call it as delta. It is sigma. So this is a way that how do we decide the high symmetry points using xcrystal is another tool. For every software, whether you are working with the BAS, you are working with the Quantum Espresso, or you are working with the Win2K, you must have insight about all these high symmetry points. So these all I have mentioned in my YouTube channel, all is the scripts. So are you familiar that what I'm talking?
Yes.
So then similarly you can model the, and there is another very important tool, just we call that as a GDIS. So I want to give you a little complete flavor of what we call DFT tools. So the command to install GDIS is a sudo apt get install GDIS. on my system it is already installed, so it's already installed. Say GDIS, it is open. Now suppose I want to can anyone tell me what is the lattice constant of diamond? What is the lattice constant of diamond? Anyone? Lattice constant of diamond.
Sir, it is around 3.5.
3.5 angstrom. Okay. So let me help you to how to model a diamond structure. So for diamond, I go to here, model contents. In model editing, I took one atom and add atom. Okay, I go to the new model and then I go here and put a one atom and say this is a carbon atom. So I just put it C here and enter, and I place its pose 0 0 0 0, then enter. For Y it is again 0 and then again 0, right? Then let me confine this atom in a box. Say I go to here and then I go to the transformations, and it is 3.5, and diamond is basically FCC structure, a typical FCC structure, but two FCC structures are merged among each other. So that means what is for FCC lattice constant is what? 3.5. 3.5 will be here because FCC for it is 3.5. It's like FCC. Its lattice vectors are FCC. So 3.5 is here and 3.5 will be here, right? And then alter lattice periodicity and say, so one atom is confined here. Now what I will do, I will put one more atom inside it, add one more atom here, and this atom will be where? So one atom is at 0 0, another atom is at 0.25, another atom is also 0.25, and another atom is again at the 0.25. And what about this? Oh, sorry. Add, delete. Go to the add item. Okay. I come to the normal mode. I just deleted it. So that means one atom is here. Okay. It should be 0.525. And then again, let me come to this one, 0.25. So these are the two atoms. Now one atom is at 0, another atom is at 0.25. I have idea about this structure, so I just save it as just let me call it as diamond dot fdf. I just saved it and just closed it, and then again opened in GDIS. It is diamond dot fdf. If you want to see this is a diamond like structure, but I don't think lattice constant of diamond is 3.5. Just a minute. Lattice constant of diamond. Yeah, it is 3.567. Yeah, it's fine. Okay.
son of so and so, I am father of so and so. This is all stupidity. Na karmana na prajaya. Dhanena. I have lots of bank balance. What is the use? You come to me in the hospital, I'll tell you.
So can I share my screen? Am I
Not
audible?
yet. Yes, sir, you are audible, but we cannot see
Okay,
the
okay.
screen.
I'm
Now it
just
is.
sharing. Okay.
Yeah.
Now my screen is visible.
Yes, yes.
So I made a structure, as I told you. It's a FDF file I can make with the help of this. So it is a diamond.fdf. If I want to see this, say GDIS diamond dot yeah 3.6.2. Yeah, this is it. This is the structure which we are getting. Say this is the structure. So if I repeat it, it's like a diamond like structure. So this is the file which I shared with you. So another very interesting thing which I tell you, because in the morning session somebody asked me about the periodicity, and if I understand periodicity, actually this structure is repeating itself in all the directions. Structure is repeating itself in all the directions. So as I take example of let me take example of any atom. Say for example, let me take example of silver. Okay, I open GDIS, I go to uh, new model, and then I go to the model editing, and in the model editing, say I just added a one atom, and say it is Ag, silver atom is there. Basically, I have to place this atom in the zero, and the zero means origin of the, or you can either put it in the center of the box. It hardly matters. And what are the lattice constant of it? Uh, Say lattice constant of this will be in the diamond like structure I am little bit wrong somewhere, so I selected say in the diamond like structure, sorry, in the FCC structure, lattice constant is 0 0.5, 0 0.5 and the 0 0.0. It is 0 0.0, 0 0.5 and it is 0 0.5, then it is 0 0.0. No. Yeah, it is 0 0.5, 0 0.0 and 0 0.5. This is the lattice vectors. And lattice constant is 4.0, suppose. This is the lattice constant. So if I am putting lattice constant 1 here, this is another way, means if lattice constant is 1.0, then what should be the values of the lattice vectors? Means half of this means it is 2.04, 2.04, it is 0 0.0, it is 0 0.0, 2.04, 2.04, it is 2.04, it is 0 0.0, 2.04. These are the lattice vectors which we have to keep in mind. So keeping this in mind, what we will do, we will put lattice vectors here. Is this clear, this point? Either I can follow this procedure or I can follow this procedure. But when I am doing things with the GDIS, I have to follow this procedure. Is this clear to you or not?
No, sir. Actually, how to calculate? How you calculated this 2.04?
It is basically half of this.
Okay.
When lattice constant is this,
Okay.
here
Okay.
0.5, right?
Okay. Got it.
Yeah. So basically I halved it. Now it's clear. Okay. So let me proceed further. Yeah, it is 2.04 here, 2.04 here, and then 2.04, and then 2.04, and 2.04 here, and 2.04 is here, and alter periodicity 3, and this is it. So this is basically our silver atom. This is silver atom. And see, it's a very interesting thing which we have to keep in mind now. I come to the normal mode, I go to here again, I go to images, and when I replicating it, this is the replication of this. So that means this single atom is behaving like a bulk material. My emphasis on the point is that a single atom is behaving like a bulk material. But I want to design a two-dimensional material. I want to design a two-dimensional materials. So for that, what should I do? For two-dimensional material, uh, I just do one thing. I just saved it first of all, right? I saved it. It is ag underscore 1.f. If say it is the name of my file. I saved it. Now I opened it. This is it, this file, and I just copied it with another name. Say I called it as ag underscore 2, and the way in which I made this as say if I go to this file, then it is like this, right? This is our structure, and see, these are the parameters, these are the default parameters, and the file which I shared with you, that has that doesn't contain default parameters, but that file contains the parameters which are optimized. So now what do we do? Let us do one thing. In this file which I renamed, I can do one thing. I just change this dimension as, I say dimension along this as 22.04 along z direction, right? Along z direction, I changed the dimension. It's a large enough, and I saved it. So when I saved it and again opened it using GDIS, he underscore 2.ftf. So what it will be? So that means along z direction there is a large vacuum, and if I repeat this along z direction, then is it visible to you all?
Yes, sir.
So see, this is one atom and this is another atom. The separation between these two atoms is large enough so that they are not interacting with each other. Their interaction is least. So that means this single atom is now behaving like a two-dimensional material because it is interacting with itself only along these two, its interaction is least. So this is clear from this picture now. If I keep on replicating, see, these are the replicas. So that means now it is behaving like a 2D sheet of it. And how will you decide the vacuum region? Actually, 12 to 15 angstrom distance is the sufficient to make it a interaction free picture. And if I give vacuum along two directions, suppose I am again renamed it, and I am doing it in say 3, and just again opened it, and I am putting vacuum along two directions. Sorry, along means x-axis. Sorry, along y-axis. Say 22 here, 22 here. Then what will happen? It starts behaving like a one-dimensional chain. It starts behaving like a. So periodicity can be taken care like this in any DFT code. Say now it will become a one-dimensional because it is not interacting with itself in the two directions. Say I'm go to the images, and in images you will get C. Say it is a isolated chain. Only one direction it is isolated. Let me decrease this number. Yeah, and let me decrease this number. See, it is a chain. And if you give vacuum in along all the three directions, then it will become a zero-dimensional system. So I think things are clear now. It's not about siesta, it's basically about every code which we are studying.
Yes, sir, it's much clear. The only thing is because of lack of that Linux thing, I could not practice it on hand. So, sir, are the things almost the same way done in Quantum Espresso also, or Burai software also?
Actually, structure designing is similar to it, or the high symmetry points. Actually, the syntax will be different.
Okay.
Syntax is different. The way of input file, the format may be different, but rest of the things, the way you high symmetry points choose, the way you dimensionality will change, these things will remain the same. Even that has, quantum espresso has own repositories for its pseudo potentials. Siesta will also provide you the repository for pseudo potentials also. But I suggest if you make your own pseudo potential, test your own pseudo potentials, then that will be much more helpful.
And how do we make that pseudo potentials? That would be defined at your website as well.
Yeah, I have mentioned that. Even I even few workshops on my college. I put everything on YouTube and recorded everything. And today's lecture is also recorded by the organizers, so that will also be there.
Okay, and but on your website, I was not able to find out your ResearchGate profile, because at one point you mentioned you suggested us to go through the papers available at your ResearchGate.
Paper are on the ResearchGate. I have not mentioned the ResearchGate link there.
Okay, okay.
Yeah, but my CV is also there. You can get my research papers there also on
Okay.
my website. My CV is also
Yes,
there.
sir, that is there. That is there. So,
Yeah.
would it be possible for you to mention your ResearchGate profile in the chat box here?
Just a minute. Let me check. Uh,
I have already shared in the group,
okay.
WhatsApp group, as well as in the chat box.
Oh, yeah. That's great.
Sir, shall I ask you a doubt?
Pardon?
Hello?
Yeah.
Yeah.
Shall I ask you a doubt, sir? Actually, my doubt is like when you explain the things to us, um, you have changed the lattice parameters for different values ranging from 3.5 till
Okay.
maximum value. And is it similar to the geometrical optimization that we are doing in the VASP? Is it like that?
Yeah, Baspida will also do in this way. Means first of all you have to find out the cell parameters, and after that you will optimize the atoms. Uh,
So is it my doubt is it like the geometrical optimization for which uh, lattice point the energy is minimum?
yeah, energy is minimum. That's the structure actually.
Okay. So in the VASP initially we do the geometrical optimization. In that also for different positions of the atom where the
Yeah.
energy is the minimum. So it is the same kind of thing, no?
Yeah. Actually two three things are there in all the codes. Either you will structure the dimensions of the cell first of all. There is a one possibility. Another, you will optimize cell parameters and atoms as well as. That is the variable. You have to make the variable cell too in that case. Means cell will also changing and the atoms are also changing their positions. But in that case, what will happen if you in that way? Then atom is also changing and structure is also changing. Then your crystal structure will also change.
Okay.
So better you first of all relax the cell parameters and after that relax the atoms. Because when you switching from 2D 3 dimension to 2 dimensional material, so in that case, first of all you will relax the cell parameters, then you relax the atoms. After that, again relax the cell parameters, then again relax the until CG opt move will become zero. Conjugate gradient method will become zero.
Okay. Sir, that's fine. And the second doubt is, if I want to work with a new material, usually how do we start with the FDF file? How do we create the FDF file?
Okay, so if you have, say, inside of the atoms, you can use some experimental databases, or if you have, say, suppose, if you know some three-dimensional material and you have to make a new two-dimensional material, that may be the beginning because you have to take some reference point somewhere, or if you want to design some new structure, suppose, then you have to test all the parameters. Say if you want to check new material, say it may be whether it is existing in the FCC, BCC or simple cubic, then you have to try all the possibilities. Then the where you will get the global minima, that is your structure.
Okay, sir. Means we have to take the reference from the research papers. That's what.
Yeah,
Yeah.
you have to take some say if you want to design a let me give you one example.
Okay, sir.
Let me take example of molybdenum sulfide, MOS2. So
Okay.
MOS2 is basically a yeah, MOS2 is basically a three-dimensional material, and it is a van der Waals material. So we know that what is the structure of MOS2 three-dimensional material experimentally, it is well known to us. So what we did when we say we do not know whether MOS2 is existing in the 2D layer or not. So that means what we will do, we will create a vacuum along the z direction, and then we have taken that unit cell. But for the 2D material, then you optimize the cell dimensions. So when you get the cell dimensions, then these cell dimensions are different than the bulk, little bit, but it is approximately closer to that. So once you get the cell dimensions A and B, because along C it is the vacuum. So when you get the A and B for that, you will optimize it. So you get a rough estimate of it. Then what you did, you again optimize the cell, optimize the atoms. Means now in this case you will get the minima for CG step 0. Then once you get this minimum, optimize the atoms by taking CG step 100 or 1000. Right? Now atoms has changed their positions according to two-dimensional structure. Say it is optimized in the 70 CG steps. This is one thing. If it optimized in CG steps, that means
Yeah.
we have to again re-optimize A and B, again get the minima until CG step will become 0 automatically. So we keep on repeating. So that means this is a way that how we have switched from 3D to 2D material, and we have now got the lattice parameters corresponding to 2D structure. And once 2D structure is there with you, then you have to, whether that system is stable or not, you have to do phonon calculations, whether that system is thermally stable or not. Because once you give an idea of new structure, then that structure must be thermally stable. So for thermal stability, you have to do the phonon calculations.
Sir, in the Patron calculation, what is the reflection of stability? What should be the value of that
Okay,
calculation?
actually phonons are basically energy versus K, they are like this. They are like this. Suppose they are like this. But if you get negative value, say it is the 0 and these are the positive values, but if you get some negative value somewhere here, if it is like this, so that means if negative values are there, that means structure is not thermally stable. So it should have positive values here.
Okay, okay, okay.
Yeah.
And sir, one more doubt, the last doubt. Actually, I want to try the trans-siesta for the transport calculation for a new
Okay.
material. So in that, while I just started only, I am not at all familiar with the siesta coding. I just want to familiarize with the siesta, then go to the trans-siesta. I think so.
Transient. Okay. Okay.
Then, so there, in order to run the code,
Uh,
actually, we have I think three set of files. One is for the core, and the other is for the electrodes. One is in the left side, and the
Actually,
other is
it
in
is basically a device region is there, and the electrode regions are there, right? It is the left
yeah,
lead,
yeah, yeah,
and it is the right lead. That's what we will do.
yeah. So
Hmm.
in the transistor, the things are similar. In the codes, like codes, syntaxes and codes are like CST only.
Actually, you have to first of all, uh, actually, its periodic boundary conditions are different in transistor. You can call transistor, or even another code is there. ATK is also there. ATK will also do for us.
Okay.
Similar.
Quantum
So,
ATK.
quantum ATK, yeah. So, basically, both are similar, but the actually the periodic boundary condition is different in both the codes. How? Actually, the electrode region is periodic. This is also
Yeah.
periodic,
Sir,
and this
one
region is
interruption.
non-periodic.
Is it infinitely periodic or finite?
Yeah,
Infinite.
this is infinitely periodic along this direction and this direction,
Okay.
but not towards this direction. And similarly with this
Okay.
region. But this is non-periodic. It is actually the device region.
Hmm.
So that's the difference between it. So first of all, you have to relax it separately. You have to relax it separately. You have to relax it separately. And when you brought these closer, means you are bringing this towards this side and this towards this side, and there is some region around it. So they will also relax, because when we brought these closer, the few layers of this and few layers of this will interact with each other, and similarly few layers of this will interact with each other. So you have to relax, and so this is known as the buffer zone. And beyond this buffer zone, two or three layers of electrode will also be interacting with it, and after that, the region which you are getting after that, this should be identical. This region should be identical to each other. Then you have to run the CST.
So in the code, are we treating the atomic positions of all these regions together, or
Pardon?
we treat them separately?
I'm not getting your voice. I'm not
What I
getting
was
your voice,
asking
but
is, yeah,
first
yeah,
of all, you have.
yeah, yeah. Yeah, actually, I was asking that,
Yeah, I'm
are
saying
we
that first
treating
of all,
all these three
yeah.
regions together or separate?
First of all, you have to left and right are the similar. So whatever is your left electrode, that will remain your right electrode. So when you make a final file, and you have to separately do calculation for this device region, say if you are putting some molecule inside it, then that should be relaxed, right? So but when you make a device region, so your left lead and the electrode, because in the beginning of your FDA file, your left electrode should be there, setup should be there. Then after that you put your device region, then you put your right electrode, and right electrode should be similar to this. It must be the replica of your left electrode, but it is displaced along the z direction. Basically it is yours. Let me take it. 1 2 3 4 5 6 atoms are there, and say 8 atoms are there, and one just a minute, uh, say 1 2 3 4 atoms are there, and after that say 1 2 3 4 5 6 7 8 atoms are there. So what you will do, say this is your actual device region, but this device is also interacting with few of the electron with it. So what you will do, you will along with the electrode this and this is your device actually. Are you getting my point?
Yeah, sir. Yeah, I'm getting.
And then you will do calculation, electrode calculation only for this part, for left lead. And this is actually your Z direction. So you have to put your atoms along Z direction in the Cartesian format, not in this fractional form. One thing, your atom should be placed in Cartesian format. And when you do calculation for transistor, you have to freeze this zone, and then relax these automatically, and after that you run siesta for transistor calculation. Then after that you will run TV trans. This is the basic procedure which we have to follow.
Okay, sir.
Is this clear now?
In your yeah, almost clear, sir. I got the idea. Do you have any YouTube tutorials for the transistor too?
I have made a video. It is it's a workshop conducted by Professor Mohanlal Verma,
Okay.
and on that I have made lectures on it,
Okay, sir.
and that was recorded.
Okay, is it available in your channel, sir?
Yeah, it is available on that. It is Professor Mohanlal Verma from Bhilai. He has there, and I made lectures on that. Even the theory lecture is also there, and hands-on session is also recorded. And not on my YouTube channel, actually.
So I have one question regarding simulators. May I put up my question?
Yeah. Yeah.
Thank you. Thank you for the permission. So actually, just as there are many simulators where we uh, try to have an idea about what type of properties this particular material would be expressing, if we know the lattice parameters and other structures. Is there any simulator? Is it possible to have the reverse of it? Suppose I want a particular material having this much conductivity and this much optical properties and all those things. So, is it possible that we have any simulator which can suggest us which materials we can add together and what should be the possible lattice structure to get this particular end result as the optical properties and conductivity properties and electrical properties? Am I clear in my question?
Yeah. You want which code? How we will decide that? Yeah, actually, uh,
Hello?
it is not so important. Important thing is your band structure. A band structure, whether it is a conducting or not. If your large number of bands are crossing the Fermi energy, so that means it is a very good conductor. One thing. Another thing is that whether your band, how much is your band gap. On the basis of band gap, you will decide that what type of optical properties this material must have, whether it is a direct band gap, indirect band gap, and even as I talked about here in the transistor, even transistor, if one band is crossing the Fermi energy, and if it is a quantum conductor, then its quantized conductance is 1 g naught for one band. If three bands are crossing, then it is typically 3 g naught. So it is the band structure, it will basically tells us about its properties.
Okay. Okay, sir. Thank you, sir.
Hello, sir.
So any other query?
Sir, hello, sir.
Yeah.
Actually, sir, we make 3D to 1D actually. Randomly, we are decreasing the X and Y or anyway, or we have to optimize this value.
No, you have to optimize the value.
Where we get minimum energy.
Yeah, wherever you will get the minima.
Sir, in the PDF you shown earlier, the title was various properties of bulk gold. So why is it only bulk gold? Can we also change things? We can go to nano crystalline materials.
Yeah, you can go to the nanomaterials. Even I show you with my slide, which I told you that in the morning. Say I have taken, say, this is the monolayer of CRS2 or CRSE2. If you try to look at this structure, and I have made ribbons out of it. This is the arm zigzag ribbons, and these are the armchair ribbons. And then I did calculations for the flakes, zero dimensional flakes are there. So this is my input structure when I cut it into, and then this is the relaxed structure. So you can switch from the 2D to 1D and the 0D. So this is a
Okay,
periodic
so
along one direction only.
yeah, how can we make differentiate between this in the code?
Code, actually, if you put a large vacuum along one direction, say if you are working with a uh, if you are working with, suppose, three-dimensional material, and if you put a large vacuum along one direction, then it will become automatically two-dimensional material. And if you put a vacuum along two directions, it will become a one-dimensional material. And if you put a vacuum or the large lattice structure along three directions, then it will become a zero-dimensional material. And in the CST, it will mention whether it is a bulk, it is a 2D layer or 1D. It is in the out file. It is mention. It mentions. For example, yeah, it is there. Let me go to the out file. Its system type is there. It was somewhere here. Yeah, it is written. System type is bulk. Actually, siesta will automatically, even siesta is one advantage. And if you don't give any lattice parameters, means lattice constant, lattice parameters, if you do not give, then it automatically run calculation for zero dimensional system. Is this clear to you, as I do?
Yes, sir.
Sir, I have one question. Hello.
Yeah.
Sir, in this we are performing calculation for electronic part, but how we will do the calculation for the excitome?
It will not do calculations for excitone siesta. It will do ground state properties only.
Okay, okay.
And it will do optical calculations by taking a base of basically if you want to do optical calculations for this, then yeah, it will do this way. It will use first order perturbation theory. So H is this, H naught is the for the ground state, and V naught is
Yes.
the photon causing the perturbation, which is the perturbing Hamiltonian,
Okay.
perturbing part. So once you got the band structure, it will use the band structure to calculate the imaginary part of dielectric function. This is the equation for this. And this is the Fermi functions for initial and the final states. And once it is there with us, because we are having a band structure, we know that the bands below the Fermi energy and above the Fermi energy. So using that, we can use Kramer-Kronig relations to find out the real part of dielectric function. And once these two parameters are there with us, means imaginary part can be calculated from the band structure, and
Okay.
from that you will calculate the real part of dielectric function. And after that you can calculate these parameters also, reflectance,
So
absorption of,
yes, imaginary part gives the information of absorption, and the real part reflection information we can get. It is like that.
yeah, it's like that.
And for the exciton, how we can do the calculation then if it is not? If
It will not do for that excitons. I've not seen anywhere. Even I'm searching few years back, but I didn't get any idea about it.
Because in this MOS2 or all these things you are talking about, these materials, in this excitons are formed when we excite these materials using optical pulse. A exciton, B exciton, that I have heard in one presentation. So that's why I am asking this.
Okay. Me, I don't know. With Siesta, it is not possible. There are some other codes which will do optical calculations, but Siesta will not do. Even still in 5.0, they included time-dependent density functional theory, but I have not still explored that because there is some issues with 5.0.
So this
Right now.
in time dependent this calculation, in this we take account of excitation basically.
Probably.
Yes,
It is
because
possible. Yeah.
electronic excitation basically we can say.
Yeah.
Okay.
Sir, with your permission, one more doubt, sir, actually.
Hanji. Yeah.
Um, so when you explain the geometrical optimization, what I got is we can do the geometrical optimization in two different way, like in a loop. First, we change the lattice parameter, we find the minimum, then we change the atomic positions.
Yeah.
So how do we that do the atomic position change? The lattice parameter you already shown us for different values. We find the minimum.
Actually, as it, I understand your question. Actually, the way when, as say, I know that my structure is FCC. Should remain FCC. FCC means one atom should be at the corner and another atoms must be at the what we call one atom is at the center, corner, and three atoms at the face center. Say if I am keep changing or I allow my simulation to change the atoms, then what will happen? Structure may relax, but what will happen? Those face-centered atoms may change their positions a little bit. If they change their positions a little bit, so that means at that time my FCC behavior will change, right? This is one thing. So that means in that case, I have to simply optimize the lattice constants, not atoms. Atoms are not allowed to move. Atoms are fixed, one at the center and three at the face center. But say, if I am switching from say 3 dimension to 2 dimension, then what will happen? I am creating a vacuum according to 3 dimension. 2 dimension, but my atoms are placed with respect to 3 dimension structure, right? So then first of all I relax the cell parameters, and then I asked in another part, once I got the minima according to those cell parameters, I allowed my structure to relax, means the minima, the lattice constant according to which we got the minima, I got that structure, and then I allowed to change the position of the atoms for that particular lattice constant. But if atoms are relaxed in the 0 CG step, then there is no problem. But if they will take more time, that means atom has moved their positions in that 2 dimensional say phase. That means now lattice constant need to be changed. Then I again get the minima according to that also, and I keep on doing this in this way, so that I will get CG of will become 0. Means I keep on repeating this step time and again. Let me give you
Specifically, sir, let me ask the doubt like this. Specifically, my doubt is how do we actually change the atomic position? Lattice parameter, actually, we were entering the
well,
values.
how do we do that? Okay, at me, if
So,
CG steps.
so I have one
Yeah.
question. Actually, whatever you have explained, like that, we can study the structural phase transition, because if some structural phase transition is happening in any material, then this DFT calculation we do at the 0K, if structure is not unstable, if we allow to relax the atom position, then we can get the new structure corresponding to the phase transition, right?
You can say like that, but in the context of this siesta code, if you put CG step 0, then atoms do not move.
Yes, yes, but when we
Right?
allow
When
that,
you CG, just a minute, when CG step is 1000, then means atoms will move. For example, I am having a say thin sheet of atoms, right? This is the sheet of atoms, and I want to absorb some molecule over it. So I want to absorb some molecule here. So that means I will put a geometrical constraint over it that sheet atoms do not move. But this must move. So that means I put CG. So what I will do in this case, when I want to do adsorption over it, I freeze the atoms of this sheet. There is an option in the code to put some constraint. I freeze those atoms, and then when I brought another molecule towards it, so that means what will happen? I have to give a CG step 1000, because in the environment of this molecule will move and it will relax. Zero step is not sufficient for me. So it is your problem whether you have to do calculation for CG step 0 or CG step 1000. It varies from problem to problem.
Okay, sir, I got it. We control it using the CG step.
so
Yeah.
same
That's what you are
same
saying.
type of
Yeah,
thing we
thank
can
you.
follow when we are changing the temperature and the structure is changing. So in that,
For temperature, you have to do molecular dynamic simulations. For you have to apply some thermostat. Noise thermostat is there. Noise Hoover thermostat is there. For this, you need to. I think I didn't do those calculations because that require a high computation power, and for that you have to equilibrate the energies. So,
okay,
you
but the concept is same, I think. We cannot
do
do.
with the help of siesta also those things also.
Yes.
Yeah, concept will remains the same. Concept will remain, only the additional flags are there with which you will change the temperature. But the number of simulation, because when you increase the temperatures, atoms will move.
Yes, sir.
Here we are doing the ground state calculation, but when you do change the temperature, atoms will move. So you have to see the equilibration energy curves for that.
Okay, sir.
So in this software, what is the temperature it is considered? I mean,
It's a
at
0
what temperature?
Kelvin. It's a ground state properties.
Okay.
All the codes will do ground state properties until unless you will allow it to do molecular dynamic simulation. For that, you have to apply some Nose Hoover or Nose thermostat or any other thermostat.
And for molecular dynamic simulation, which software we use?
You can use siesta code also.
Okay.
But you require more computation cost. Large number of items are there. It depends upon what type of computational capacity do you have. According to that, I will suggest you have to choose the software or the problem.
So we can do that in WASP also, I think.
You can also do it in the past also.
Okay.
But if you go to the past, very few problems are done for the one-dimensional systems. WASP is better for 2D or 3D, but for 1D and 0D, WASP will not do calculations. So very few paper I have seen for the WASP.
Actually, my system is quasi 2D, so I think it will work for that.
Yeah, WASP will work. If machine is better, you have, then it will work for you. And WASP expert will tell you better because I'm only working with the CS stuff.
Sir, shall I ask you a suggestion on my material? Actually, my material is a quasi one-dimensional class of material.
Okay.
And I want to study the
So,
transport properties of those materials.
yeah, siesta will do better. or
Okay, sir.
80K.
And okay. So my question is, if I have a material, the suitable electrodes, how do I choose them? What is the criteria for
Pardon?
that? Is it suppose I have a material like
What
TiO3, something like that. Which
TiO3?
one will be the suitable electrode? How do I choose that?
Electrode may be anything. They say for electrode you can take any metallic system. Even you can take a graphene, you can take a gold electrodes. Electrode means a electron reservoir. So any electronic material, even what people will do, because it's very difficult to do work with this transistor. So sometimes people will take same material as they are treating. Same material they will treat as electrode sometimes.
So I
But
have one
actually,
question.
but you have to say you have to use a metallic.
Yeah. So I have one question. Like how we can know, like for our system, like plain wave or the siesta is good. Like whether the quantum espresso or the siesta is good. So like here, even for 3D, we can use siesta, right?
Yeah.
Yeah, but for 3D material, it's always recommended this plain way based like quantum.
Actually, siesta will also do good results, but you have to do little more work on it. You have to optimize. You must first of all optimize the parameters. So people prefer actually plain way based codes for that. But siesta will also do very good things.
Yeah, yeah.
Yeah.
So for 1D, like how much vacuum we should put, like around how much
Actually,
Armstrong in siesta?
Actually, it's 12 to 15. Even you can give 30 angstrom, that will also work. Siesta doesn't have any problem. But 15 angstrom must vacuum. Means if you repeat two, say, means two structures, if you repeat, and if you large vacuum, then it should be minimum 15 angstrom.
Okay. It won't take much time, like even if we increase the vacuum,
No, no,
comparing to quantum espresso.
no, it will not. Vacuum will not affect siesta. How much vacuum? Even you can give, even if you do adsorption, you have to give a large vacuum even when you do adsorption, because there is one layer and over it you are putting some molecule here. So the molecule is large enough. So that means at least say 10 angstrom diameter is the same molecule, and say layer is here. So up to layer 2 angstrom above is this. So 12 is this one. So above it, you can give even 12 more. So that means 30, 40 angstrom, it will work very well.
Yeah. Yeah. Okay.
And computational cost is remains the same.
Yeah. Okay.
So any query? Another?
Sir, so far we have talked about a single atom material. Can we do like metal oxides or more complex systems?
Yeah, we can do any type of systems. But it should be periodic.
Yeah.
And crystalline. Non-crystalline, we cannot work.
Okay.
Because for non-crystalline, actually large number of atoms we have to take care, and it require a very huge computational cost.
Sir, one more doubt.
Yeah.
So it's again, it's about the transistor structure FTF file. I have two electrode. One is left, one is right, and at the center I have the material.
Okay.
Material. So when I create the FDF file, actually from left to the boundary of the material, there is one set. Then there is a material set of maybe 6 atoms or 7 atoms. Then again, the left will be repeated in the reverse manner. The boundary will be first, then it will be extended to the infinity.
Yeah.
So, actually, how possibly we will make this information? I mean, where the atoms are there in the atomic position information, how do we make it? That is my doubt. I have referred many papers, but I am not getting proper idea regarding this.
Basically, as I told you a few minutes back,
Okay, okay.
as I shown a one-dimensional structure there, and then that will help you. And actually, you have to take care one thing, that the left and right should be. So you have to check when you repeat left electrode and right, it will replicate itself on one side, and
Yeah,
similarly right side will also. And in between region, that doesn't matter how will you place, but it should be in the symmetric order, I mean, left and right. Say
yeah,
uh, this one thing, this is say your electrode is this one, and this is your device. You just put it from here, and then you just translated it from here to here simply.
yeah,
It's a translation actually along that axis, and this coordinates in the Cartesian form.
yeah.
Simple. This is the idea.
Okay, but actually, for that, if I consider the entire structure as a one unit, then there is no periodicity, na? In from left electrode till the
But it's not, but it is periodic. So for that, it will take it will take help of non-equilibrium green function.
okay, 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 okay.
It is non-equilibrium green functions it will use. So
Yeah, yeah.
this
NEGF,
is
no?
Landauer Whittaker approach they will use.
Okay, okay.
For that, you can follow the mesoscopic physics by Supriyo Datta, or quantum transport. There is the 2 3 books by Professor Supriyo Datta. You can follow those books.
Yeah, yeah, yeah. Okay, sir.
Yeah, yeah.
Thank you very much.
Okay.
I have one concern. Uh, as I was not able to download Sista and I was watching through these, I will do this afterwards, maybe in
Okay.
next coming days. So one of the concern is that how would I attempt the assignment which you have suggested us to do on.
So, how should I say about that? You can do with others also.
I don't know if this is the problem only with me or with others as well.
Mhm. I think this you have to ask organizer. That will be better, because they asked me to give some assignment. Then I suggested this is, I think. Yeah. Actually, there is another workshop in Kurnool for that 1 week workshop on Siesta and DFT in the month of July.
Okay. Can you
It is
please send us the
it
link
is
for the details so that if possible we
in
would.
the I shared with the organizers
Okay,
with that
okay.
in the, yeah.
And that workshop would also be online or offline, sir?
Or that is offline actually, because in the online there is a little bit very difficult to
Yes, of
show
course.
people.
That
Yeah,
is the problem. That is the problem.
this is
So
1 weekend that is dedicated to Siesta actually.
I would request the organizers to send us the details of that workshop as well.
I will send
Okay.
that
Thank you, sir.
now. Yeah.
We would see the organizers' perspective of attempting at this assignment. Okay. Thank you, sir.
So any other query? I think I have to stop now.
Thank you. I thank the invited speaker for giving a detail on the Sista software. So here we have already past the time. It is around 1 p.m. So after 1 hour, we will meet again In that, the session will be chaired by Captain Ritu Rasing and the speaker is Deepak Upadhyaya. So let us meet at 2 p.m. again. So it is a lunch break. So once again, I thank the invited speaker Arul sir for his insightful insightful knowledge giving about the SISTA and how to use it. Even that SISTA is allowed to use in the nano scale also. So thank you once again, sir, for your
Thank you for
time.
inviting.
Okay. Yogen sir, please
Thank you,
off
sir.
the recording.